Collision domains are a fascinating aspect of networking, especially in half-duplex Ethernet networks. In these setups, devices share the same bandwidth, leading to potential collisions. Think of hubs. They operate at layer 1, creating a single collision domain. Every device connected to a hub is essentially in the same boat, competing for bandwidth, which can lead to chaos. Now contrast that with switches. Operating at layer 2, switches create separate collision domains for each port. This means each device can communicate without stepping on each other's toes, significantly reducing collisions. Then there's CSMA-CD, or Carrier Sense Multiple Access with Collision Detection. This protocol helps manage those collisions when they do happen, ensuring that devices can detect and recover from them efficiently. The takeaway? More collision domains like those in switched networks lead to fewer collisions and better overall network performance. It's all about keeping the data flowing smoothly.
Data link layer, layer 2. It will provides reliable data transfer across a physical link by organizing bits into frames and managing errors in the physical layer. Functions of layer 2. MAC, Media Access Control, sublayer, manages device addressing through MAC addresses and controls who can access the shared medium. LLC, Logical Link Control, sublayer, provides error checking, flow control, and frame synchronization. Example of Layer 2 protocols: Ethernet, PPP, Point-to-Point Protocol, Wi-Fi, IEEE 800 and 2.11. Example Layer 2 devices: switches, bridges. Application layer, Layer 7. Role: provides the interface between the application software and the network, enabling end-user services and network-related functions. Functions: allows applications to communicate with the network and access network services. Provides network services directly to end users or applications, such as email, file transfer, and web browsing. Example protocols: HTTP, Hypertext Transfer Protocol; FTP, File Transfer Protocol; SMTP, Simple Mail Transfer Protocol; DNS, Domain Name System. Presentation layer, Layer 6. Role: transforms data into a format that the application layer or the network can use, ensuring that the data sent by one system is interpretable by another. Functions: handles data translation, encryption/decryption, compression, and formatting. Converts data between formats, such as text, images, and video. Example protocols: SSL/TLS, Secure Sockets Layer/Transport Layer Security, ASCII, for text encoding, JPEG, image formatting.
When we talk about domain names, it's fascinating to dive into the specifics. First, we have the fully qualified domain name, or FQDN. This is the complete address that includes both hostname and the domain, like server.example.com. It's like your home address on the internet, specific and complete. Then, there's the top-level domain, or TLD. This is the last part of a domain name, such as .com, .org, or .net. Think of it as the category of your address. Next up is the second-level domain, or SLD, which is the main part right before the TLD. For instance, in example.com, example is the SLD. Finally, we have subdomains, which are prefixes added to a domain for different services. For example, blog example.com is a subdomain of example.com, allowing you to create distinct sections of your website. Each type of domain name plays a crucial role in how we navigate the web, making it easier to find exactly what we're looking for. When we talk about domain names, it's fascinating to dive into the specifics. First, we have the fully qualified domain name, or FQDN. This is the complete address that includes both the host name and the domain, like server.example.com. It's like your home address on the internet, specific and complete. Then there's the top-level domain, or TLD. This is the last part of a domain name, such as .com, .org, or .net. Think of it as category of your address.
Just picture a vast network spreading across the globe, connecting devices, systems, and individuals in a beautiful symphony of communication. The interconnections within this network act as the threads that intricately weave this web, allowing for the seamless transfer of data from one point to another. Whether it's a simple home network or a complex global infrastructure, these interconnections play a crucial role in our ability to share resources, collaborate, and stay connected in this digital age. Much like a serene garden where each plant supports the growth of others, networking interconnections create a smooth and continuous flow of information that enhances our lives and facilitates global connectivity.
A network router is a device that directs data packets between different networks, such as local area networks, LANs, and wide area networks, WANs. Routers are essential in both home and business networks, as well as in the global internet infrastructure, for connecting multiple networks together and ensuring data reaches the correct destination. Routers operate primarily at the network layer, layer 3, of the OSI model, which enables them to make forwarding decisions based on IP addresses. Router will interconnect the networks and it will choose the best path to reach destination/remote networks. A network switch is a device that connects multiple devices, like computers, printers, servers, within a local area network, LAN, and directs data to the correct destination device on the network. Switches operate primarily at the data link layer, layer 2, of the OSI model.
When a switch receives an Ethernet frame, it springs into action. First, it extracts the source MAC address from the frame header. This is where the magic begins. The switch then updates its MAC address table, also known as the CAM table, storing that source MAC address along with the corresponding port number. If it finds that MAC address already listed but on a different port, it updates the entry, keeping everything current. Next, the switch checks the destination MAC address. If it finds a match in its table, it forwards the frame directly to the correct port. If not, it resorts to flooding the frame to all other ports, a process known as unknown unicast flooding. This ensures that the frame reaches its destination, even if it means creating a bit of extra traffic. Once the frame is on its way, the switch keeps its MAC address table tidy. Each entry has an aging timer, typically around 300 seconds. If no frames are received from a MAC address within that time, the switch removes it from the table, freeing up space for new addresses. This efficient process keeps the network running smoothly and minimizes unnecessary congestion. When a switch receives an Ethernet frame, it springs into action. First, it extracts the source MAC address from the frame header. This is where the magic begins. A network switch operates at layer 2 of the OSI model, where the magic of data transfer happens. It uses MAC addresses to forward frames efficiently, ensuring that data reaches the right destination without unnecessary delays. Imagine a bustling post office, where each package is labeled with a unique address. That's how a switch manages traffic, by reading these MAC addresses and directing frames precisely where they need to go. But here's where it gets interesting: the MAC learning process. As frames flow through the switch, it dynamically builds a MAC address table, also known as the CAM table. This means the switch learns which devices are connected to which ports, reducing unnecessary traffic. Instead of broadcasting every frame to all ports, it sends it only to the intended recipient. This not only minimizes congestion, but also boosts overall network performance. So, the next time you enjoy a seamless online experience, remember the unsung hero working behind the scenes, the network switch, efficiently managing data like a pro. A network switch operates at layer 2 of the OSI model, where the magic of data transfer happens. It uses MAC addresses to forward frames efficiently, ensuring that data reaches the right destination without unnecessary delays. The Internet Protocol, or IP, is the backbone of our digital communication, operating at the network layer of the TCP/IP model. It assigns unique IP addresses, like the familiar 192.168.1.1 for IPv4, or the more complex 2001 ODB8, 8A2E03707334 for IPv6, ensuring every device can be identified on a network. But it doesn't stop there. IP also routes data packets, determining the best path for them to travel across interconnected networks. Imagine sending a letter without knowing the address. That's what IP prevents. It encapsulates data from the transport layer, adds essential metadata, and even fragments larger packets to fit network limits. And here's the kicker. IP is connectionless and offers best effort delivery, meaning it doesn't guarantee that your data will arrive in order or even at all. That's where higher layer protocols like TCP come into play. With IPv4 and IPv6, we're looking at a world of nearly 4.3 billion addresses versus virtually unlimited options. And while IPv4 can be complex, IPv6 simplifies things for efficiency and security. So, the next time you send a message or stream a video, remember the vital role IP plays in making it all possible. Console password is a crucial security feature for network devices, acting as a gatekeeper to the console port. This physical interface, whether it's a serial port or USB, provides direct access to the device. Think routers, switches, or firewalls. By implementing a console password, we prevent unauthorized users from gaining local access, ensuring that only those with the right credentials can configure or troubleshoot the device. Imagine connecting to the console port with a terminal emulator like PuTTY. The moment you plug in, the device prompts you for a password. Enter the correct one and you're in, accessing the command line interface. But without that password, access denied. This simple yet effective measure adds an extra layer of security, especially if the physical device is compromised. In the world of network security, a console password is not just a good practice, it's essential. A console password is a crucial security feature for network devices, acting as a gatekeeper to the console port. This physical interface, whether it's a serial port or USB, provides direct access to the device. Think routers, switches, or firewalls.
Welcome to our video on computers, the incredible electronic devices transforming our world through data processing and storage. Computers execute instructions from software programs, enabling them to perform countless tasks with efficiency and precision. From basic calculations to complex simulations, computers have the capability to handle a wide variety of functions. Their ability to process large amounts of information quickly and accurately makes them indispensable in today's world. Industries across the globe rely on computers as essential tools for their operations and advancements. From healthcare to finance, education to entertainment, computers drive innovation and productivity everywhere. Join us as we explore how computers continue to shape and revolutionize our daily lives and future.
IPv4 addresses are fascinating as they're divided into 5 distinct classes, each serving unique purposes. Class A is designed for large networks like ISPs with a range from 1.0.0.0 to 126.0.0.0. Imagine the vastness of connections possible. Then we have Class B, catering to medium-sized networks spanning from 128.00.0 to 191.255.0.0. This class strikes a balance, perfect for universities or large businesses. Next up is Class C, which is ideal for small networks, covering 192.0.0.0 to 223.255.255.0. Think of your home or small office network. This is where it thrives. Class D takes a different turn, reserved for multicast, with a range from 224.0.0.0 to 239.255.255.255, enabling efficient data distribution to multiple recipients. Finally, we have Class E, the experimental class, ranging from 240.0.0.0 to 255.255.255.255, reserved for future innovations. Each class plays a vital role in the intricate web of the Internet, showcasing the brilliance of network design. Store and forward switching is a fascinating process in networking. Imagine this. When a switch receives an Ethernet frame, it doesn't just pass it along blindly. It first checks the entire frame for errors using a method called cyclic redundancy check, or CRC. If everything checks out, it forwards the frame. This meticulous error checking ensures that only valid frames make it through, significantly reducing network congestion caused by corrupted data. However, there's a trade-off. This method introduces higher latency, since the switch must wait to receive and process the entire frame before forwarding it. Despite this delay, store and forward switching shines in enterprise networks where error-free transmission is crucial, like in VoIP and video conferencing. In these environments, preventing the retransmission of corrupted frames is essential for maintaining smooth communication. So, while it may slow things down a bit, the reliability it offers is invaluable. Store and forward switching is a fascinating process in networking. Imagine this. When a switch receives an Ethernet frame, it doesn't just pass it along blindly. It first checks the entire frame for errors using a method called cyclic redundancy check, or CRC. If everything checks out, it forwards the frame. Cut-through switching is a fascinating technology that enhances network performance. It works by reading just the destination MAC address from the Ethernet frame header and forwarding the frame immediately, skipping the error checking process. This means lower latency and faster forwarding, making it perfect for high-speed applications. Imagine stock trading or gaming networks where every millisecond counts. Cut-through switching shines in these environments. However, it's not without its drawbacks. Since it doesn't check for errors, corrupted frames can slip through, potentially increasing network congestion if too many bad frames are sent along. So, while it's a speedster in low latency scenarios, careful consideration is needed to manage those risks. Cut-through switching is a fascinating technology that enhances network performance. It works by reading just the destination MAC address from the Ethernet frame header and forwarding the frame immediately, skipping the error checking process. Fragment-free switching is a fascinating hybrid approach to network switching. It reads the first 64 bytes of a frame before forwarding it, which is crucial because most errors occur within that initial segment. This method strikes a balance between speed and error detection. You get lower latency than traditional store and forward methods, while still filtering out those pesky collision fragments. However, it's not without its trade-offs. While it's faster than pure cut-through switching, it does have slightly higher latency and won't catch all errors, just those in the first 64 bytes. This makes fragment-free switching ideal for gigabit Ethernet networks where you need that sweet spot of speed and some level of error checking. It's all about optimizing performance while minimizing the risk of forwarding bad frames. When a device sends a frame, the switch springs into action, learning the source MAC address and updating its MAC table with the associated port. This is the heart of how switches operate. Now, when it comes to forwarding frames, the switch uses the destination MAC address from that table. It's like a well-organized mailroom, ensuring that data get to the right destination without delay. But what happens if a MAC address hasn't been used for a while? The switch has a solution for that too. It employs an aging process, removing stale entries after a specified period, keeping the table fresh and efficient. And here's where it gets interesting. If the switch encounters a destination MAC address it doesn't recognize, it doesn't panic. Instead, it floods the frame to all ports, except the one it came from, ensuring that the data still gets a chance to reach its destination. This dynamic process keeps networks running smoothly, making sure communication flows seamlessly. When a device sends a frame, the switch springs into action, learning the source MAC address and updating its MAC table with the associated port. This is the heart of how switches operate. Dynamic MAC learning is a fascinating process that powers the efficiency of network switches. Imagine a switch as a smart traffic cop, meticulously observing every device that connects to it. As data flows in, the switch inspects the source MAC addresses of incoming frames, like noting down license plates of cars passing by. Each time a device sends traffic, the switch records its MAC address and the specific port it arrived on in its MAC address table. This isn't a one-time event. It happens continuously and automatically, allowing the switch to adapt to changes in the network. As devices come and go, the switch updates its records, ensuring that data is always sent to the right destination. This dynamic learning not only optimizes network performance, but also enhances security by keeping track of who's who in the network. It's a seamless dance of data, making our connected world run smoothly. Dynamic MAC learning is a fascinating process that keeps our networks running smoothly. Imagine a switch that's like a savvy librarian, automatically learns MAC addresses of incoming frames in real time. When a device sends a frame, the switch inspects the source MAC address and updates its MAC address table, noting which port the frame arrived on. This means that when future frames come in, the switch knows exactly where to send them. But there's more. These dynamic MAC addresses aren't permanent. Out, usually between 100 to 600 seconds. If no traffic is detected from a specific during that time, it gets removed from the table. This aging process ensures that the MAC address table stays current and efficient. Dynamic MAC learning is the go-to method for switches because it's automatic and requires no manual setup. It's like having a smart assistant that keeps everything organized, allowing devices to communicate seamlessly on the network. Dynamic MAC learning is a fascinating process that keeps our networks running smoothly. Imagine a switch that's like a savvy librarian, automatically learning the source MAC addresses of incoming frames in real time. Static MAC addresses are a powerful tool in network management. When a network administrator manually configures a static MAC address, they're essentially locking in a specific address to a designated switch port. This means that unlike dynamic entries that can age out, a static MAC address remains in the MAC address table until someone decides to change or remove it. This is particularly useful for securing critical devices like servers and printers. By ensuring that traffic meant for these devices is always directed to the correct port, we can effectively prevent unauthorized access and spoofing attempts. The advantages are clear. Static MAC entries enhance security since they can't be altered automatically by other devices. Plus, they can significantly improve network performance, especially for high-traffic devices that require stable, constant connectivity. In a world where network integrity is paramount, static MAC addresses are a vital strategy for maintaining control and security. Dynamic MAC learning is a fascinating feature of network switches. It automatically learns the MAC addresses of devices connected to it, which is incredibly convenient. However, these addresses age out after a certain period, making it ideal for devices that frequently change or don't require secure traffic. Think of it as a flexible approach, perfect for everyday devices in a bustling office. On the other hand, we have static MAC addresses. These are manually configured by an administrator and don't age out, providing a layer of security for high priority or critical devices. Imagine a server or a security camera that needs consistent access without the risk of being dropped from the network. Static MAC addresses ensure that these vital connections remain intact, safeguarding your most important assets. In short, dynamic MAC learning offers flexibility, while static MAC addresses deliver security. Each has its place in the network, and understanding their differences can help you optimize your setup effectively. Port security on a switch is like having a bouncer at a club. ensuring only the right guests get in. It restricts access to a network port based on MAC addresses, which are unique identifiers for devices. When you configure port security, you're telling the switch, only these devices can connect here and connect. If an unauthorized device tries to sneak in, the switch can take action, like blocking it, shutting down port, or even sending an alert. This feature significantly boosts network security by preventing unauthorized access and keeping your data safe. Think of it as a digital gatekeeper, ensuring that only trusted devices can communicate through that port. It's a simple yet powerful way to protect your network from potential threats. Port security on a switch is like having a bouncer at a club, ensuring only the right guests get in. It restricts access to a network port based on MAC addresses, which are unique identifiers for devices. Port security is essential for safeguarding our networks, and one key feature is MAC address limiting. By specifying how many MAC addresses can be learned on a port, we can control access. For instance, limiting a port to just 1 or 2 MAC addresses ensures that only trusted devices connect. Then we have static MAC addresses, where you manually configure specific addresses that are allowed. This means only those devices can connect, providing a solid layer of security. On the flip side, dynamic MAC addresses allow the switch to learn and store addresses automatically, perfect for environments with frequent device changes. Now, what happens if there's a violation? The switch can take several actions. It can protect the network by dropping packets from unknown MAC addresses without shutting down the port. Or it can restrict access by logging the incident while keeping the port operational. The most secure option? Shutdown. This disables the port entirely and generates an alert. Lastly, sticky MAC addresses offer a blend of flexibility and security. When enabled, the switch learns and saves MAC addresses even after a reboot, allowing for easy management while still keeping unauthorized devices at bay. Port security is all about balance, ensuring connectivity while maintaining a fortress around our networks. Port security is a game changer for network safety. It prevents unauthorized devices from sneaking onto your network, giving you control over which devices can connect. Imagine being able to limit access to only trusted devices. This is crucial for maintaining a secure environment. Plus, with robust logging and alerting capabilities, you can easily track any unauthorized access attempts, keeping you one step ahead of potential threats. Another significant advantage is that it helps prevent MAC spoofing. By ensuring only known devices can connect, you reduce the risk of malicious actors impersonating legitimate devices. However, it's essential to manage port security carefully. If you set the maximum number of allowed MAC addresses too low, you might inadvertently block legitimate devices. In larger networks, this can get tricky, but using dynamic or sticky MAC learning can simplify management. Balancing security and accessibility is key to a robust network strategy. Port security is a game changer for network safety. It prevents unauthorized devices from sneaking on your network, giving you control over which devices can connect. Imagine being able to limit access to only trusted devices. This is crucial for maintaining a secure environment. When a switch detects a port security violation, it has 3 key actions to choose from. First, there's the Protect mode. Here, the switch drops packets from any unknown MAC addresses but keeps the port active. No notifications, just silent protection. Then we have the Restrict mode. This one not only drops those packets but also generates a log entry, keeping you informed while still allowing legitimate traffic to flow. Finally, we reach the Shutdown option. This is the heavy artillery. When a violation occurs, the port is administratively disabled and an alert is sent out. It's the most secure choice, ensuring that unauthorized access is swiftly cut off. Each action has its place, depending on how tight you want your network security to be. Imagine an office where everyone is shouting across the room. It's chaotic, right? Now picture a VLAN, like creating separate rooms for different teams. A VLAN, or virtual local area network, allows devices to communicate as if they're on the same physical network, even if they're miles apart. This segmentation transforms a sprawling network into organized sections, enhancing performance and boosting security. By isolating sensitive data and reducing broadcast traffic, VLANs ensure that only the right people have access to the right information. It's like having a VIP lounge in a crowded club, exclusive, efficient, and secure. VLANs are essential in today's interconnected world, making networks smarter and more manageable. Imagine a bustling office where everyone is shouting across the room. It's chaotic, right? Now, picture a VLAN, like creating separate rooms for different teams. VLANs, or virtual local area networks, are a game changer in networking. Imagine grouping devices not by where they sit, but by their function or project. For instance, all accounting computers can be on the same VLAN, even if they're on different floors. This logical grouping enhances collaboration while keeping things organized. Now let's talk about traffic separation. VLANs create virtual boundaries, meaning devices on one VLAN can't just chat with devices on another without a router or layer 3 switch. This separation reduces broadcast traffic and boosts security, making your network more efficient. Each VLAN defines its own broadcast domain. Devices within the same VLAN can communicate directly, while those on different VLANs need routing. This setup minimizes unnecessary traffic and optimizes performance. Finally, we have Layer 2 and Layer 3 VLANs. Layer 2 VLANs operate at the data link level, managed by switches, while Layer 3 VLANs involve routing between VLANs, handled by routers or Layer 3 switches. This distinction is crucial for effective network management. VLANs truly revolutionize how we think about network design and efficiency. VLANs, or virtual local area networks, are a game changer in networking. Imagine grouping devices not by where they sit, but by their function or project. For instance, all accounting computers can be on the same VLAN, even if they're on different floors. VLANs are a game changer for network management. Imagine slicing a massive network into smaller, manageable pieces. That's exactly what VLANs do. They reduce broadcast domains, which means less congestion and better performance. Security is another big win. By isolating sensitive data, VLANs keep guest users away from the corporate network, minimizing the risk of unauthorized access. Think about traffic management. When you group similar devices, like a busy marketing team, into their own VLAN, you prevent unnecessary slowdowns from other departments. Plus, managing a network becomes a breeze. Instead of fiddling with each device, you can make changes at the VLAN level, enhancing flexibility and simplifying troubleshooting. And as your network grows, moving devices between VLANs is seamless. No need to mess with physical cabling. VLANs truly empower network administrators to create efficient, secure, and scalable networks. VLANs are a game changer for network management. Imagine slicing a massive network into smaller, manageable pieces. That's exactly what VLANs do. They reduce broadcast domains, which means less congestion and better performance. Security is another big win. By isolating sensitive data, VLANs keep guest users away from the corporate network, minimizing the risk of unauthorized access. In a company, organizing your network with VLANs is like creating separate rooms for different teams. Imagine VLAN 10 for marketing, VLAN 20 for sales, VLAN 30 for HR, and VLAN 40 for IT. Each VLAN is assigned to specific switch ports, so devices connected to those ports are part of the designated team. This setup allows seamless communication within each VLAN, but if marketing wants to chat with sales, they need a router to bridge the gap. Now, how do we keep track of all this traffic? That's where VLAN tagging comes in. When data travels between switches, it gets tagged with a VLAN ID using 802.1q tagging. This little identifier ensures that switches know exactly where to send the traffic, keeping everything organized and efficient. So, with VLANs, not just managing a network, you're creating a well-structured environment for collaboration. In a company, organizing your network with VLANs is like creating separate rooms for different teams. Imagine VLAN 10 for marketing, VLAN 20 for sales, VLAN 30 for HR, and VLAN 40 for IT. Each VLAN is assigned to specific switch ports, so devices connected to those ports are part of their designated team. This setup allows seamless communication within each VLAN, but if marketing wants to chat with sales, they need a router to bridge the gap. Voice VLANs are essential for optimizing voice traffic in our networks. Unlike standard data traffic, voice traffic is incredibly sensitive to delays. That's where voice VLANs come in. By designating a specific VLAN for IP phones and VoIP services, we ensure that voice packets are prioritized over regular data. This means lower latency and a smoother experience during calls. Imagine a busy office where everyone is streaming videos while someone is trying to make an important call. Without a voice VLAN, that call could drop or sound choppy, but with it, voice traffic gets the VIP treatment, ensuring crystal clear communication. In essence, voice VLANs help maintain the quality of our conversations, making sure that every word counts, even in the busiest environments. Prioritizing voice traffic isn't just a technical choice. It's a commitment to clear and reliable communication. Voice VLANs are essential for ensuring high-quality communication on our networks. They prioritize voice traffic, which is crucial for maintaining call quality. By implementing quality of service, we minimize delays, jitter, and packet loss, allowing conversations to flow smoothly. Separating voice devices, like IP phones, into their own VLAN isolates voice traffic from data traffic. This separation significantly enhances call quality, reducing interference from other network activities. Another key feature is Power over Ethernet, or PoE. This technology allows us to power IP phones directly through the Ethernet cable, simplifying installation and reducing clutter. Finally, managing voice traffic becomes a breeze. With IP phones assigned to their own VLAN, we can easily apply policies, shape traffic, and monitor performance without the complexities of mixed traffic. Voice. VLANs truly elevate our communication experience. They prioritize voice traffic, which is crucial for maintaining call quality. By implementing quality of service, we minimize delays, jitter, and packet loss, allowing conversations to flow smoothly. Separating voice devices, like IP phones, into their own VLAN isolates voice traffic from data traffic. This separation significantly enhances call quality, reducing interference from other network activities. A data VLAN is essential for keeping our digital lives running smoothly. Imagine it as a dedicated highway for standard data traffic. Think of your computer workstations, servers, and all those daily networking tasks. This VLAN is where the magic happens, handling everything from web browsing to file transfers and email communications. When you send an email or download a file, it's the data VLAN that ensures your data travels efficiently and securely. By segmenting this traffic, we reduce congestion and improve performance, allowing for faster response times and a more reliable connection. In a world where seamless communication is key, the data VLAN is the unsung hero, quietly managing the flow of information that keeps our businesses and lives connected. It's not just about data, it's about creating a smoother, more efficient experience for everyone involved. Data VLANs are essential for managing our network traffic efficiently. They primarily carry regular data, which means they don't require the same low latency or high priority as voice traffic. This separation is crucial. By isolating data on its own VLAN, we reduce congestion and enhance overall network performance. It's like giving each type of traffic its own lane on the highway. No more bottlenecks. Even though data traffic isn't as critical as voice, applying quality of service, or QoS, is still vital. In high-traffic environments, optimizing network usage ensures that everything runs smoothly. So, while data VLANs may not steal spotlight, they play a key role in keeping our networks secure and efficient. Data VLANs are essential for managing our network traffic efficiently. They primarily carry regular data, which means they don't require the same low latency or high priority as voice traffic. Using both voice and data VLANs is a game changer for network performance. Imagine this. Voice traffic needs priority treatment, and by dedicating a VLAN just for it, we can ensure minimal latency and packet loss. This means clearer calls and happier users. Plus, troubleshooting becomes a breeze. When voice traffic is separated from data, pinpointing issues is straightforward. You can deploy specific monitoring tools tailored for the voice VLAN, making diagnostics efficient. And let's not forget about security. By segregating voice and data traffic, we can implement distinct security policies for each. This protects sensitive voice communications while enhancing overall network performance. In a world where every call counts, using both voice and data VLANs isn't just smart, it's essential. frame is like a well-organized package that travels across the network highway. Picture this. It's a structured bundle of data, meticulously crafted to ensure communication between devices. Each frame contains a header, which is like the address label, guiding the data to its destination. Inside, you'll find the source and destination MAC addresses, ensuring that the right devices are talking to each other. Then there's the payload, the actual data being sent, whether it's a video, a file, or a simple message. Finally, the frame wraps up with a trailer that checks for errors, making sure everything arrives intact. This entire process happens in the blink of an eye, allowing our devices to exchange information seamlessly. Understanding Ethernet frames is key to appreciating how our digital world stays connected and efficient. The preamble, a crucial byte sequence, plays a vital role in communication between devices. Picture this: a stream of data flowing between two machines, and they need to be perfectly in sync. That's where the preamble comes in. It's like a rhythmic handshake, consisting of alternating ones and zeros. Think of it as a digital drum beat. This pattern, 10-1-0-1-0-10, helps the receiver's clock align with the incoming data stream, ensuring that every bit is captured accurately. Without this synchronization, chaos could ensue. Data could be misread or lost entirely. So, next time you send or receive information, remember the unsung hero of digital communication, the preamble, keeping everything in perfect harmony. The preamble, a crucial 7-byte sequence, plays a vital role in communication between devices. In the world of Ethernet, the start of frame delimiter, or SFD, is a crucial byte that plays a pivotal role in data transmission. Represented by the binary sequence 10-1-1-1, this single byte follows the preamble and signals the start of the actual frame. Think of it as a green light for data. Once the SFD is detected, the receiving device knows it's time to focus on the real information coming next. Without this clear marker, frames could blend together, leading to confusion and errors in communication. The SFD ensures that the data is interpreted correctly, maintaining the integrity of the information being sent. So, next time you send or receive data over Ethernet, remember that the SFD is there, quietly doing its job, ensuring everything runs smoothly and efficiently. The destination MAC address is a crucial part of how data travels across a network. Picture this. Every device connected to a network has a unique identifier, known as a MAC address, which is made up of 6 bytes. This address acts like a digital postal address, ensuring that the data packets reach the right destination. When a frame is sent out, it carries this MAC address, guiding it through the maze of devices on the local network. Without it, data would be like a letter without an address, lost in the digital ether. Each MAC address is unique to Network Interface Card, or NIC, making it essential for communication. So, next time you send or receive data, remember that behind the scenes, the destination MAC address is working hard to ensure your information arrives safely and accurately at its intended device. It's a small detail, but it plays a massive role in the seamless connectivity we often take for granted. The source MAC address is a crucial part of network communication, consisting of 6 bytes that uniquely identify the device sending a data frame. Think of it as a digital fingerprint. When your device sends information, it tags that data with its MAC address, allowing the receiving device to know exactly who sent it. This is essential for a couple of reasons. First, it enables the recipient to respond accurately, ensuring that data flows smoothly back and forth. Second, it plays a vital role in troubleshooting. If something goes wrong, the MAC address helps pinpoint the source of the issue, making it easier to resolve. So, next time you send or receive data, Remember that little 6-byte identifier is working behind the scenes, keeping your network communication efficient and reliable. The source MAC address is a crucial part of network communication, consisting of 6 bytes that uniquely identify the device sending a data frame. Ether type is a fascinating 2-byte field that plays a crucial role in networking. It tells us exactly which protocol is being carried in the payload of a frame. For instance, if you see the value 0800, you know you're dealing with IPv4, the backbone of internet communication. Then there's 0x0806, which signifies ARP, the protocol that helps devices discover each other's MAC addresses on a local network. And let's not forget 0x86DD, which indicates IPv6, the modern solution to our ever-growing IP address needs. Each of these values is like a secret code, guiding data through the complex web of the internet. Understanding ether type is key to grasping how our digital world communicates seamlessly. Ether type is a fascinating 2-byte field that plays a crucial role in networking. It tells us exactly which protocol is being carried in the payload of a frame. When we talk about payloads and data transmission, diving into the heart of what makes communication happen. Picture this. A payload can range from 46 to 1500 bytes, carrying the essential information that a sender wants to share with a receiver. This could be anything from HTTP request to a file transfer. Now here's the catch. If your data is smaller than 46 bytes, it doesn't just float around aimlessly. Instead, padding is added to ensure that the entire frame hits the minimum Ethernet size of 64 bytes. Think of it like a cozy blanket wrapping around a small package, making sure it fits snugly in the delivery system. This padding might seem trivial, but it plays a crucial role in maintaining the integrity and efficiency of data transmission. So, next time you send a message or download a file, remember that behind the scenes, your payload is doing some serious work to ensure everything arrives just as it should. When we talk about payload and data transmission, we're diving into the heart of what makes communication happen. Picture this. A payload can range from 46 to 1500 bytes, carrying the essential information that a sender wants to share with the receiver. This could be anything from an HTTP request to a file transfer. The frame check sequence, FCS, is a crucial component in ensuring data integrity during transmission. Picture this. As data packets travel across networks, they carry a 4-byte FCS, which holds a cyclic redundancy check, or CRC value. This CRC is like a digital fingerprint, calculated from the frame's contents, but it cleverly excludes the preamble and the FCS itself. When a receiving device gets a frame, it doesn't just accept it blindly. It recalculates the CRC based on received data and compares it to the FCS value. If they match, it's a green light, error-free. But if there's a mismatch, it's a red flag. The frame gets tossed out, and a retransmission is requested. This process is vital for maintaining the reliability of our data communications, ensuring that what we send is exactly what we receive. In the world of networking, the FCS is the unsung hero, tirelessly working behind the scenes to keep our connections clean and accurate. Let's break down a net frame that carries an IPv4 packet. First up, we have the preamble, which is 7 bytes of alternating ones and zeros. Think of it as the frame's warm-up act, setting the stage for synchronization. Next, the start frame delimiter, or SFD, is just 1 byte, signaling the official start of our frame with a distinct pattern. Now onto the heart of the frame, the destination MAC address, 6 bytes long, like 0.1A, 2B.3C, 4D5E, tells us where the data is headed. Right next to it is the source MAC address, also 6 bytes, like 0.1F, 2A, 3B, 4C, 5D, revealing where the data is coming from. Then we hit the ether type, a 2-byte field that identifies the protocol. 0x0800 indicates we're dealing with IPv4. Following that, we have payload, which could be around 100 bytes of actual IPv4 data, the main content of our frame. Finally, we wrap it up with the frame check sequence, or FCS, a 4-byte CRC that ensures everything is error-free. And that's a quick journey through the anatomy of an Ethernet frame. Let's break down an Ethernet frame that carries an IPv4 packet. First up, we have the preamble, which is 7 bytes of alternating ones and zeros. Think of it as the frame's warm-up act, setting the stage for synchronization. Next, the start frame delimiter, or SFD, is just 1 byte, signaling the official start of our frame with a distinct pattern. Now, onto the heart of the frame. The destination MAC address, 6 bytes long, like 00.1A, 2B, 3C, 4D, 5E, tells us where the data is headed. Right next to it is the source MAC address, also 6 bytes, like 0.1F, 2A, 3B, 4C, 5D, revealing where the data is coming from. A trunk port on like a superhighway for data, allowing multiple views to travel seamlessly over a single physical connection. Imagine trying to fit all your friends into one car for a road trip. Everyone's got their own space, but you're all heading in the same direction. That's what a trunk port does. It carries traffic from various VLANs, keeping them logically separated while efficiently using the network's resources. This is crucial for maintaining security and performance in larger networks. So, whether it's voice, video, or data, a trunk port ensures that everything flows smoothly without any collisions. It's the backbone of modern networking, making sure that all those virtual lanes can coexist without a hitch. VLAN, specifically through the 802.1q protocol, is a game changer in network management. Imagine a trunk port as a busy highway, carrying traffic from multiple VLANs. Each data frame that travels this highway gets a special tag, inserted right between the source MAC address and the ether type fields. This tag is like a license plate, identifying which VLAN the frame belongs to. When a switch or router receives this tagged frame, it instantly knows where to direct the traffic, ensuring that data reaches the right destination without confusion. This efficient tagging not only optimizes bandwidth, but also enhances security by isolating traffic between different VLANs. So, next time you think about network efficiency, remember the silent hero of VLAN tagging, keeping our data organized and flowing smoothly. VLAN tagging, specifically through the 802.1q protocol, is a game changer in network management. Imagine a trunk port as a busy highway, carrying traffic from multiple VLANs. Imagine you have multiple. Trunking is a game changer in network design. Imagine you have multiple VLANs, like VLAN 10 for marketing and VLAN 20 for sales. Without trunking, each VLAN would need its own physical connection, leading to a tangled mess of cables and ports. But with trunk ports, we can streamline communication across different switches. A single trunk link carries traffic from all VLANs, allowing devices in different segments to talk to each other effortlessly. This not only saves on hardware costs, but also simplifies network management. So, whether it's sharing files between departments or accessing shared resources, trunking makes it all possible, efficiently and effectively. It's the backbone of a well-organized network. When we talk about trunk ports in networking, we can't overlook the concept of the native VLAN. By default, it carries traffic for all VLANs on a switch, but the native VLAN is a bit special. It's the default VLAN that doesn't get tagged as it travels across the trunk link. Typically, this is VLAN 1, but you can change it if needed. So, what does this mean? Well, frames from the native VLAN are sent without any tags, making them stand out. This can lead to confusion if not managed properly, especially when different VLANs are communicating. If a switch receives an untagged frame, it assumes it belongs to the native VLAN. Understanding this distinction is crucial for maintaining a smooth network operation and avoiding potential security risks. So keep your native VLAN in check and ensure your network runs like a well-oiled machine. When it comes to networking, understanding when to use a trunk port is essential. Picture this: you're connecting switches to each other. A trunk port is your best friend here, allowing all VLANs to flow seamlessly between them. Now, think about connecting a switch to a router. If you're using a router on a stick configuration, that trunk port is crucial for sending traffic from multiple VLANs to the router. It's like having a multi-lane highway for your data. And let's not forget about switch-to-server connections. If you're dealing with a virtualized server hosting multiple virtual machines, each on different VLANs, a trunk port ensures that all that traffic is efficiently managed. It's all about maximizing bandwidth and keeping your network organized. So remember, trunk ports are the backbone of efficient VLAN communication in your network. When it comes to networking, trunk ports are essential for carrying multiple VLANs over a single link. They utilize 802.1q VLAN tagging, which allows us to efficiently manage traffic. Think of it as a highway where each vehicle represents a different VLAN, seamlessly traveling together without interference. Now, every trunk port has a native VLAN, which is the VLAN that doesn't get tagged. By default, that's VLAN 1. This is crucial because it ensures that untagged traffic is still recognized and properly routed. Configuring a trunk port is straightforward. You simply set it to trunk mode with the command switch port mode trunk. The most common protocol for this is 802.1q, though you might encounter ISL in older setups. Understanding these concepts not only optimizes your network, but also enhances communication between switches and devices, making your infrastructure robust and efficient. VTP, or VLAN trunking protocol, is a game changer in networking. Imagine managing multiple VLANs across a network with ease. That's what VTP does. It's a Cisco proprietary protocol that centralizes VLAN management on switches, ensuring that every switch in the domain has consistent and synchronized VLAN information. No more manual updates on each switch. VTP automates that process, reducing the risk of configuration errors. It operates in 3 modes: server, client, and transparent, allowing flexibility based on your network needs. With VTP, you can scale your network efficiently, keeping everything organized and streamlined. It's like having a conductor for an orchestra, ensuring every instrument plays in harmony. So, if you want to simplify VLAN management and enhance your network's efficiency, VTP is the way to go. VTP, or VLAN trunking protocol, is a game changer in networking. In the world of VLAN trunking protocol, or VTP, we have 4 distinct modes that dictate how switches interact with VLAN. First up is server mode, the default setting. Here, switches can create, modify, and delete VLANs, and any changes they make ripple throughout the network, keeping everything in sync. Then we have client mode, where switches take a backseat. They can't make any changes themselves. They simply receive VLAN information from the servers, ensuring they stay updated without any direct involvement. Next is transparent mode. This one's interesting. Switches in this mode don't engage with VTP at all. They can create and manage VLANs locally, but those changes won't affect other switches. Finally, there's off mode, where VTP is completely disabled. No VLAN information is shared or received, giving the switch a clean slate. Each mode has its purpose, shaping how VLANs are managed across the network. Understanding these modes is key to effective network management. In the world of VLAN trunking protocol, or VTP, we have 4 distinct modes that dictate how switches interact with VLANs. First up is server mode, the default setting. Here, switches can create, modify, and delete VLANs, and any changes they make ripple throughout the network, keeping everything in sync. In the world of networking, VTP, or VLAN trunking protocol, plays a crucial role in managing VLANs across switches. Picture this. All switches in a network must share the same VTP domain name to communicate effectively. Why? Because this ensures that VTP updates, like VLAN additions or deletions, are only shared among switches that belong to the same domain. If one switch is in a different domain, it won't receive those updates, leading to potential misconfigurations and network chaos. Think of it as a secret club. Only members with the same domain name can share the latest gossip. This keeps your network organized and efficient, preventing unnecessary traffic and confusion. So when setting up your switches, remember, a consistent VTP domain name is key to a harmonious network environment. Keep it uniform and watch your VLAN management become a breeze. When it comes to VLAN trunking protocol, or VTP, there are 3 versions to consider: VTP v1, VTP v2, and the latest, VTP v3. VTP v3 stands out with its impressive enhancements. First off, it supports extended VLANs, allowing for a whopping 4096 VLANs, which is a game changer for larger networks. Security is another key upgrade. VTP v3 introduces features like authentication, ensuring that only authorized devices can make changes to the VLAN configuration. Plus, it supports multiple VTP domains, giving network administrators greater flexibility and control. With VTP v3, managing VLANs becomes not just easier but also more secure and scalable, making it the go-to choice for modern networking needs. VTP, or VLAN trunking protocol, is a powerful tool in networking that helps manage VLAN information across switches. Every 5 minutes, VTP sends out advertisements to keep all connected devices in sync. Imagine a well-orchestrated symphony where each musician knows exactly when to play their part. That's how VTP operates.
When a new VLAN is created, the VTP server takes charge, instantly propagating that change to all VTP clients. This means no more manual configuration on each switch, saving time and reducing the risk of errors. It's like having a central command center that ensures everyone is on the same page. With VTP, network administrators can easily manage VLANs, streamline operations, and maintain a clean, efficient network.
It's all about keeping communication flowing smoothly, ensuring that your network runs like a well-oiled machine. VTP, or VLAN Trunking Protocol, is a powerful tool in networking that helps manage VLAN information across switches. Every 5 minutes, VTP sends out advertisements to keep all connected devices in sync. Pruning is a game changer when it comes to managing VLAN traffic on trunk links. Imagine a busy highway where only the cars need to be there can pass through. That's what VLAN Trunking Protocol, or VTP, does for your network. By intelligently filtering out unnecessary VLAN information, it ensures that only the switches that need specific VLAN data receive it. This not only reduces congestion but also enhances overall network performance. Think of it as a smart traffic cop, directing data where it needs to go and keeping the rest clear. With VTP pruning, your network becomes more efficient, reliable, and scalable, allowing you to focus on what really matters, keeping your data flowing smoothly. Pruning is a game changer when it comes to managing VLAN traffic on trunk links. Pruning is a game changer when it comes to managing VLAN traffic on trunk links. Imagine a busy highway where only the cars that need to be there can pass through. That's what VLAN Trunking Protocol, or VTP, does for your network. By intelligently filtering out unnecessary VLAN information, it ensures that only the switches that need specific VLAN data receive it. This not only reduces congestion but also enhances overall network performance. Think of it as a smart traffic cop, directing data where it needs to go and keeping the rest clear. With VTP pruning, your network becomes more efficient, reliable, and scalable, allowing you to focus on what really matters, keeping your data flowing smoothly. Pruning is a game changer when it comes to managing VLAN traffic on trunk links. is a game changer in networking. Imagine combining multiple physical links into one powerful connection. That's what Ether Channel does. It boosts bandwidth, allowing data to flow faster and more efficiently between switches or devices. But it's not just about speed, it also adds redundancy. If one link fails, the others keep the connection alive, ensuring seamless communication. Configuring Ether Channel is straightforward, using protocols like LACP or PHP to manage the links intelligently. This technology is essential for high-traffic environments, making networks more robust and reliable. So, whether you're streaming videos or transferring large files, Ether Channel keeps everything running smoothly and efficiently. Ether Channel is a game changer for network performance. Imagine boosting your bandwidth by aggregating multiple links. 4 1 Gbps links give you a whopping 4 Gbps. That's a serious upgrade, but it's not just about speed. Ether Channel also offers redundancy. If one link goes down, the others keep the traffic flowing, ensuring your network stays up and running. Plus, it intelligently balances the load across those links based on MAC addresses or IPs, optimizing performance and preventing bottlenecks. And let's not forget simplified management. Instead of juggling multiple links, you manage them as a single logical connection. It's efficiency at its best, making your network robust and easy to handle. Ether Channel is a game changer for network performance. Imagine boosting your bandwidth by aggregating multiple links. 4 1 Gbps links give you a whopping 4 Gbps. That's a serious upgrade. But it's not just about speed. Ether Channel also offers redundancy. If one link goes down, the others keep the traffic flowing, ensuring your network stays up and running. PAGP, or Port Aggregation Protocol, is Cisco's secret sauce for creating Ether channels effortlessly. Imagine you have multiple links between switches, and you want them to work together as one. That's where PAGP shines. It automatically negotiates the aggregation of these links, ensuring optimal bandwidth and redundancy without manual configuration. When two devices support PAGP, they exchange packets to determine which ports can be bundled. This dynamic negotiation means you can add or remove links on the fly without disrupting traffic. Plus, it helps prevent loops and ensures that your network remains stable and efficient. PAGP operates in two modes, desirable and auto. In desirable mode, a switch actively seeks to form an Ether channel, while in auto mode, it passively waits for the other side to initiate. This flexibility makes it a powerful tool in any network engineer's arsenal. So, whether you're boosting performance or enhancing reliability, PAGP is your go-to protocol for seamless link aggregation. LACP, or Link Aggregation Control Protocol, is a game changer in networking. Imagine combining multiple network connections into a single logical link, boosting bandwidth and providing redundancy. That's exactly what LACP does, following the IE 802.3 AD standard. It automatically negotiates the best way to bundle these links, ensuring optimal performance without manual configuration. When devices support LACP, they can dynamically detect and manage link aggregation, which means if one link fails, traffic seamlessly shifts to the remaining links. This not only enhances reliability, but also maximizes throughput. Plus, it simplifies network management, allowing for easier troubleshooting and configuration. In a world where data demands are skyrocketing, LACP is like having a superhighway for your network traffic, ensuring smooth and efficient data flow. When configuring Ether channel, it's crucial that both ends of the connection, whether it's two switches or a switch and a server, match in their settings. This means the number of links, link speeds, and negotiation protocols must align perfectly.
You can use LACP or PGP to automatically detect and bundle those multiple links into a single Ether channel, which boosts bandwidth and provides redundancy. But here's the catch. Ends need to have these protocols enabled for everything to work smoothly.
If they don't match, you might end up with a tangled mess instead of a streamlined connection. So, always double-check those configurations to ensure compatibility and keep your network running efficiently. When setting up an Ether channel, it's crucial to ensure that all links share the same speed, duplex settings, and MTU. Think of it as a team. If one player is out of sync, the whole performance suffers. This uniformity allows the Ether channel to function seamlessly, presenting itself as a single logical interface. This is particularly important in routing protocols and VLAN configurations, where consistency is key. If one link is operating at a different speed or duplex, it can lead to packet loss or even network instability. So remember, for optimal performance, keep those settings aligned. Your Ether channel will deliver the reliability and efficiency you need. When setting up an Ether channel, it's crucial to ensure that all links share the same speed, duplex settings, and MTU. Think of it as a team. If one player is out of sync, the whole performance suffers. world of Ethernet networks, Spanning Tree Protocol, or STP, plays a crucial role in stability. Imagine a bustling city with multiple roads leading to the same destination. Without traffic control, chaos ensues. That's what happens in a switched network when loops form. Broadcast storms can erupt, sending data packets spiraling out of control, creating multiple frame copies that flood the network. STP steps in as the traffic cop, identifying and blocking redundant paths, ensuring there's only one active route for data to travel. This not only prevents loops, but also keeps work running smoothly, allowing devices to communicate efficiently. By dynamically adjusting to changes in the network, STP is the unsung hero that keeps our digital highways clear and our connections reliable. In the world of Ethernet networks, Spanning Tree Protocol, or STP, plays a crucial role in maintaining stability. Imagine a bustling city with multiple roads leading to the same destination. Without traffic control, chaos ensues. That's what happens in a switched network when loops form.
In the world of networking, the Spanning Tree Protocol, or STP, plays a crucial role in maintaining a loop-free environment. Imagine a tree structure where each branch represents a connection between devices. At the top, we have the root bridge, the central hub that keeps everything organized.
All other switches connect to this root in a way that ensures there's only one active path between any two devices. This prevents loops, which can cause chaos and transmission. By dynamically blocking redundant paths, STP ensures that our network remains efficient and reliable.
So, next time you send data across the network, remember the silent guardian working behind the scenes, keeping your connections smooth and your data flowing. In the world of networking, the Spanning Tree Protocol, or STP, plays a crucial role in maintaining a loop-free environment. In the world of networking, the root bridge is the cornerstone of our topology. Picture this. Every switch in the network has a unique bridge ID, a combination of its priority and MAC address. When it's time to elect a root bridge, the switch with the lowest bridge ID takes the crown. This process is crucial because it sets the stage for how data flows through the network. Once the root bridge is established, all decisions about the network structure and paths are based on it. Think of it as the conductor of an orchestra, ensuring every note plays in harmony. If a switch has a higher bridge ID, it simply plays a supporting role, helping maintain the overall efficiency and reliability of the network. So, the next time you think about network design, remember, it all starts with that one pivotal decision, the root bridge election. In the world of networking, the root bridge is the cornerstone of our topology. Picture this. Every switch in the network has a unique bridge ID, a combination of its priority and MAC address. When it's time to elect a root bridge, the switch with the lowest bridge ID takes the crown. In networking, redundancy is key, but too much can lead to chaos. That's where Spanning Tree Protocol, or STP, comes into play. It intelligently identifies and blocks redundant paths that could create loops in the network. Imagine a busy highway with multiple routes. If every road is open, traffic jams ensue.
STP acts like a traffic cop, ensuring only the best path is active while keeping others on standby. If the primary route fails, those blocked paths spring into action, maintaining seamless connectivity. This dynamic approach not only prevents loops but also enhances network reliability, ensuring that data flows smoothly even in the face of failure.
It's a brilliant balance of efficiency and resilience in the world of networking. In networking, redundancy is key, but too much can lead to chaos. That's where Spanning Tree Protocol, or STP, comes into play. In the world of networking, BPDUs, or Bridge Protocol Data Units, are the unsung heroes of the Spanning Tree Protocol, or STP. Imagine each switch as a member of a team, constantly sending out messages to keep everyone up about its status. These BPDUs are like vital updates, information about which ports are active and which to prevent loops. When a switch receives a BPDU, it evaluates the information and makes crucial decisions about its own ports. Should it forward data or block traffic? This communication ensures a loop-free network, optimizing data flow and enhancing overall performance. So the next time you marvel at a seamless network connection, remember the BPDUs working tirelessly behind the scenes, keeping everything in sync and running smoothly. In the world of networking, BPDUs, or Bridge Protocol Data Units, are the unsung heroes of the Spanning Tree Protocol, or STP. Imagine each switch as a member of a team, constantly sending out messages to keep everyone in the loop about its status. These BPDUs are like vital updates, sharing information about which ports are active and which should be blocked to prevent loops. In the world of networking, understanding port roles in Spanning Tree Protocol, or STP, is crucial. Let's break it down. First, we have the root port, or RP. This is the port that's closest to the root bridge, acting as the primary pathway for data to travel. Think of it as the VIP lane in a busy highway, ensuring efficient traffic flow. Next up is the designated port, or DP. This port is selected to forward traffic toward a specific network segment. It's like the traffic cop, directing data where it needs to go, ensuring that every packet reaches its destination without a hitch. Finally, we have the blocked port. This one's a bit of a wallflower. It doesn't forward traffic at all. Its job is to prevent loops in the network, keeping everything tidy and organized. Without these roles, our networks could easily spiral into chaos. So, understanding these port roles is key to maintaining a smooth and efficient network. Convergence in networking is crucial after any initial setup or topology change. When Spanning Tree Protocol, or STP, kicks in, it ensures that all switches agree on the network's layout, preventing frame forwarding loops. However, STP can be notoriously slow to converge, which can lead to temporary disruptions.
That's where Rapid Spanning Tree Protocol, or RSTP, comes into play, significantly speeding up the convergence process. RSTP can react in mere seconds, allowing for a more resilient network. Then there's Multiple Spanning Tree Protocol, or MSTP, which optimizes bandwidth by allowing multiple VLANs to share the same spanning tree.
By adapting these protocols, we can maintain a stable and efficient network, ensuring seamless communication without the headaches of loops or delays. Convergence in networking is crucial after any initial setup or topology change. When Spanning Tree Protocol, or STP, kicks in, it ensures that all switches agree on the network's layout, preventing frame forwarding loops. In a spanning tree topology, the root bridge is the backbone of our network. Each switch believes it's the star of the show at first, sending out its Bridge Protocol Data Unit, or BPDU. This BPDU contains the bridge ID, which is a combination of a priority value, defaulting to 32768, and the switch's MAC address. Initially, every switch thinks it's the root bridge, advertising its own ID. As they exchange BPDUs, they start comparing their bridge IDs. The switch with the lowest ID takes the crown and becomes the root bridge. This process is crucial because it allows every other switch to calculate the best path to the root bridge, ensuring efficient data flow. The magic lies in the collaboration of these switches, each playing a part in determining the most reliable route in the network. It's a fascinating dance of data where only one can lead. In a spanning tree topology, the root bridge is the backbone of our network. Each switch believes it's the star of the show at first, sending out its Bridge Protocol Data Unit, or BPDU. This BPDU contains the bridge ID, which is a combination of a priority value defaulting to 32768 and once the root bridge is determined.
I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up. I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement. I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement.
Everything I do so instinctive and so passionate. Every word I move so descriptive like an adjective. I got a vendetta against people who patented being negative when you should be getting after it. I got facts over tracks, this and that. Spitting slow, spitting fast. I could roast, I could gas. Think I'm okay at last, but I don't know if that can erase all the past. And the pettiness, a reflection of the emptiness. Hilarious, you think you're worth my time, you're delirious. Mysterious, because you hide behind a fake exterior. Inferior, you know I'll always be a bit superior. Get off of me, this ain't no humble brag. I want you to hear words, you can say them back. I want you to feel free from the
In the world of networking, understanding port roles is crucial for maintaining a smooth and efficient data flow. Let's dive into it. First, we have the root port, or RP. This is the port on a switch that boasts the lowest cost path to the root bridge. Think of it as the VIP route for data. Each switch can only have one root port, ensuring that traffic flows efficiently toward the root. Next up is the designated port, or DP. This port is the chosen one for forwarding traffic on a specific segment. It's like the traffic cop of a network, ensuring that data reaches its destination with the least resistance. The DP is selected based on the lowest cost to the root bridge among all ports on that segment. Finally, we have the blocked port. This port is the unsung hero, preventing loops by not forwarding traffic. It's disabled to maintain order and stability in the network. Together, these roles create a robust spanning tree, keeping our networks running smoothly and efficiently. Understanding these roles is key to mastering network design. In the world of networking, the Spanning Tree Protocol, or STP, is a crucial player in preventing loops. First, we elect the root bridge. Each switch sends out Bridge Protocol Data Units, or BPDUs, and the switch with the lowest bridge ID claims the title of root bridge. Next, each switch identifies its root port, the one closest to the root bridge based on the lowest path cost. This port becomes the primary route for traffic. Then comes the designated port selection. For every network segment, STP chooses the port with the lowest path cost to the root bridge as the designated port, allowing it to forward traffic. All other ports on that segment? They're blocked to keep loops at bay. Finally, any port that isn't a root or designated port enters blocking state, ensuring a smooth and loop-free network. This is how STP keeps our networks efficient and reliable. In the world of networking, the Spanning Tree Protocol, or STP, is a crucial player in preventing loops. First, we elect the root bridge. Each switch sends out Bridge Protocol Data Units, or BPDUs, and the switch with the lowest bridge ID claims the title of root bridge. BPDUs, or Bridge Protocol Data Units, are the heroes of network communication. Every 2 seconds, switches send these vital messages to each other, sharing crucial information about their status and the overall topology of the network. Imagine a bustling city where traffic lights communicate with each other to optimize flow. That's what BPDUs do for switches. They help prevent loops and ensure that data travels the most efficient path. When a switch receives a BPDU, it assesses the network landscape, making decisions that keep everything running smoothly. This constant exchange of information is what allows our networks to adapt and thrive, ensuring connectivity and reliability. In the world of networking, BPDUs are the backbone of intelligent communication, keeping everything in sync and functioning seamlessly. BPDUs, or Bridge Protocol Data Units, are the unsung heroes of network communication. Every 2 seconds, switches send these vital messages to each other, sharing crucial information about their status and the overall topology of the network. Imagine a bustling city where traffic lights communicate with each other to optimize flow. That's what BPDUs do for switches. They help prevent loops and ensure that data travels the most efficient path. When we talk about BPDUs, or Bridge Protocol Data Units, we're diving into the backbone of the Spanning Tree Protocol, or STP. The configuration BPDU is the star of the show, carrying vital information about the bridge and the entire network topology. It plays a crucial role in electing the root bridge and calculating the optimal path to it. Without this, our network would be a chaotic mess. Then we have the Topological Change Notification, or TCN BPDU. This one's like the network's alarm system. Whenever there's a topology change, like a link failure or a new switch joining the party, it sends out a notification to alert all switches. This prompts them to reconfigure their paths, ensuring that data flows smoothly and efficiently. Both types of BPDUs work together to maintain a stable and efficient network, keeping everything connected and running like a well-oiled machine. When we talk about BPDUs, or Bridge Protocol Data Units, we're diving into the backbone of the Spanning Tree Protocol, or STP. A BPDU, or Bridge Protocol Data Unit, is essential for maintaining network topology. At its core, the root bridge ID identifies the switch acting as the root bridge, the central point in our network. This ID is crucial because it helps switches determine the best path for data. The bridge ID combines a switch's priority value, typically 32768, with its MAC address, ensuring each switch is uniquely recognized. Next, we have the root path cost, which indicates the total cost to reach the root bridge. This cost is cumulative, with the root bridge itself always set to 0. The sender bridge ID tells us which switch sent the BPDU, while the port ID pinpoints the exact port used for transmission. The message age field tracks how long the BPDU has been in circulation, preventing outdated information from causing confusion. It's paired with max age, which defaults to 20 seconds. If a switch doesn't receive a new BPDU in that time, it triggers a new election for the root bridge. Finally, hello time defines the frequency of BPDU transmissions, typically every 2 seconds, and forward delay ensures that switches don't rush into state changes, allowing for a stable network environment. Understanding these fields is key to mastering network topology. In the world of networking, every switch starts with a bold assumption. It believes it's the root bridge. Each one sends out a Bridge Protocol Data Unit, or BPDU, proudly declaring its own bridge ID as the root bridge ID. But here's where the magic happens. When switches receive these BPDUs, they compare the root bridge IDs. If a switch gets a BPDU with a low ID, it knows it's time to update its status and forward that information to its neighbors. This process continues until one switch emerges victorious, boasting the lowest root bridge ID, determined by priority and MAC address. That switch becomes the root bridge, while others adjust their paths, ensuring efficient data flow throughout the network. It's a dynamic dance of decision-making, all happening in the blink of an eye. In the world of networking, every switch starts with a bold assumption. It believes it's the root bridge. Each one sends out Bridge Protocol Data Unit, or BPDU, proudly declaring its own bridge ID as the root bridge ID. In the world of networking, every switch plays a crucial role in determining the most efficient path to the root bridge. Each switch calculates its root path cost, which is the total expense incurred to reach that bridge. As BPDUs, Bridge Protocol Data Units, travel through the network, they carry this cost information, updating the root path cost field with each hop. The switch with the lowest route path cost becomes the champion, designating its port as the route port. This is the preferred route to the route bridge, ensuring that data flows smoothly and efficiently. It's a fascinating dance of collaboration and calculation, where every switch contributes to the overall health of the network, optimizing paths and minimizing delays. Understanding this process is key to mastering network design and performance. In the world of networking, every switch plays a crucial role in determining the most efficient path to the route bridge. Each switch calculates its route path cost, which is the total expense incurred to reach that bridge. In the world of networking, understanding port roles is crucial for maintaining efficient communication. Let's dive into the designated port, or DP. For every segment connecting two switches, the port with the lowest cost to the route bridge takes the spotlight as the designated port. This is the port that actively forwards traffic for that segment, ensuring smooth data flow. Now, what about the blocked port? Any port that isn't a route port or a designated port gets sidelined into the blocked state. This is a vital safety measure, preventing network loops that can wreak havoc on performance. By strategically assigning these roles, we create a robust network topology that optimizes traffic and enhances overall stability. Understanding these roles is key to mastering network design and ensuring seamless connectivity. In the world of networking, understanding port roles is crucial for maintaining efficient communication. Let's dive into the designated port, or DP. For every segment connecting two switches, the port with the lowest cost to the route bridge takes the spotlight as the designated port. This is the port that actively forwards traffic for that segment, ensuring smooth data flow. When a network topology change occurs, a switch or link failure, it sends ripples through the entire system. This is where topology change notification, or TCN, comes into play. Imagine a TCN bridge protocol data unit, or BPDU, zipping through the network, alerting all connected devices about the change. This notification is crucial. It tells the network, hey, something's different here. Once the TCN is sent, the network kicks into gear, triggering a reconvergence process. This means all devices start recalculating the best paths for data to travel, ensuring minimal disruption. It's like a dance where everyone adjusts their steps to keep the rhythm going smoothly. Without TCNs, networks would struggle to adapt, leading to potential data loss and inefficiencies. So, the next time you experience seamless connectivity, remember the unsung hero behind the scenes, the TCN, keeping everything in sync and running smoothly. So, the next time you experience seamless connectivity, remember the unsung hero behind the scenes, the TCN, keeping everything in sync and running smoothly. Imagine three switches, A, B, and C, all working together in a network. It starts when switch A sends out its first bridge protocol data unit, or BPDU, proudly declaring itself as the route bridge. Now, switch B gets this BPDU and recognizes A as the route. It quickly forwards this information to switch C in its own BPDU. Switch C, upon receiving this, checks the route bridge ID and sees that switch A has the lowest ID. This is crucial because it means C will adjust its paths accordingly, ensuring efficient communication. In the end, each switch has a clear understanding of its role. They identify the best port to use as the route port, which is the one with the lowest cost to reach the route, and designate the appropriate ports for traffic forwarding. This seamless flow of BPDUs ensures that our network remains efficient and organized, allowing for smooth data transmission. Imagine three switches, A, B, and C, all working together in a network. It all starts when switch A sends out its first bridge protocol data unit, or BPDU, proudly declaring itself as the route bridge. BPDU timers play a crucial role in maintaining a stable network topology. Let's break it down. First, we have the hello time, where BPDUs are sent every 2 seconds by default. If a switch doesn't hear from the root bridge within the max age of 20 seconds, it assumes something's gone wrong and starts the process of electing a new root bridge. This is vital for network resilience. Next up is the max age timer, which ensures that outdated BPDUs don't linger around and confuse the network. If a BPDU is older than the max age, it gets tossed out. This keeps the network clean and efficient. Finally, we have the forward delay, which dictates how quickly ports can transition between STP states. This delay is essential for preventing loops and ensuring a smooth flow of data as ports move from listening to learning and finally to forwarding. Understanding these timers is key to mastering spanning tree protocol and ensuring your network runs like a well-oiled machine. BPDU timers play a crucial role in maintaining a stable network topology. Let's break it down. Subnetting is a fascinating process that transforms a large network into smaller, manageable subnets. Imagine a bustling city where each neighborhood has its own identity. This is what subnetting does for networks. By dividing an IP address into two parts, we create a network portion that identifies the broader area and a host portion that pinpoints individual devices within that area. Take IPv4 addresses, for example. The subnet mask like 255.255.255.0 plays a crucial role here. It tells us which part of the address is the network and which part is reserved for devices. With the first 3 octets representing a network, we can efficiently manage traffic and enhance security. This not only optimizes performance, but also ensures that we make the best use of our available IP addresses. Subnetting is like organizing a massive library into sections, making it easier to find exactly what you need without getting lost in the chaos. Subnetting is a game changer for network management. First off, it maximizes IP address usage. Instead of letting those precious addresses go to waste in a sprawling network, subnetting allocates them more efficiently, ensuring every address counts. Then there's security. By isolating network segments, we limit exposure and access, making it much harder for threats to spread. And let's not forget about management. Smaller subnets are a breeze to handle. Troubleshooting becomes straightforward when you're dealing with a compact segment rather than a massive network. Plus traffic congestion? It's significantly reduced. With data confined to specific subnets, the overall network runs smoother. Subnetting isn't just a technical necessity. It's a strategic advantage that keeps our networks efficient and secure.
A bit, or binary digit, is the fundamental building block of all digital data. It's fascinating to think that every piece of information we interact with, images, videos, and even text, is ultimately represented by a series of bits, each being either a 0 or a 1.
In the realm of IP addressing, these bits come together to form unique addresses for devices on the internet. Take IPv4, for instance. It's made up of 32 bits, which allows for about 4.3 billion unique addresses. That sounds like a lot, but with the explosion of devices, we quickly ran out of space. Enter IPv6, boasting a whopping 128 bits. That's enough addresses to give every grain of sand on Earth its own unique IP. It's incredible how something as simple as a bit can underpin the vast, interconnected world of technology we rely on every day. IP, or Internet Protocol, is the backbone of how data travels across the internet and local networks. Imagine every device connected to the internet has its own unique address, like a house on a street. That's what IP does. We have 2 main versions, IPv4 and IPv6. IPv4 is the classic, using 32 bits, and you'll recognize it by its dotted decimal format, like 192.168.1.1. But with the explosion of devices, we needed more addresses, leading to IPv6, which boasts a whopping 128 bits and uses a hexadecimal format like 2001 0DB8 85A3 2000-882E03707334. This upgrade not only expands our address space, but also enhances security and efficiency. So, next time you connect to the internet, remember the vital role IP plays in keeping everything connected. IP, or Internet Protocol, is the backbone of how data travels across the internet and local networks. Imagine every device connected to the internet has its own unique address, like a house on a street. That's what IP does. An IP address is like a digital address for your device, split into 2 essential parts: network bits and host bits. The network bits tell us which network we're on, while the host bits pinpoint the specific device within that network. Think of it as a mailing address. Your street name is the network, and your house number is the host. Subnet masks, often seen in dot decimal format like 255.255.255.0, define this division. They help routers understand where to send data. Then there's CIDR notation, which simplifies things even further. For example, 192.168.1.024 indicates that the first 24 bits are network bits. This means we have 256 possible addresses in that network, perfect for small to medium-sized networks. Understanding this division is crucial for effective network management and ensuring smooth communication between devices. An IP address is like a digital address for your device, split into two essential parts: network bits and host bits. The network bits tell us which network we're on, while the host bits pinpoint the specific device within that network. Think of it as a mailing address. Your street name is the network, and your house number is the host. CIDR, or Classless Interdomain Routing, revolutionized how we think about IP addresses. Imagine an IP address like 192.168.1.024. That slash followed by 24 tells us that the first 24 bits are dedicated to the network, leaving just 8 bits for devices within that network. This flexibility allows for more efficient use of IP addresses compared to the old class-based system, which was rigid and wasteful. With CIDR, we can create networks that fit our needs precisely, whether we have a handful of devices or thousands. It's like customizing your own pizza, no more one-size-fits-all slices. This innovation not only conserves IP addresses, but also enhances routing efficiency, making our internet experience smoother and more reliable. CIDR, or Classless Interdomain Routing, revolutionized how we think about IP addresses. A subnet mask is like the secret sauce of networking, breaking down a 32-bit IP address into two essential parts: the network and the host. Think of it as a digital address label. For instance, when you see 255.2555.255.0, it tells you that the first 24 bits are reserved for the network, while the last 8 bits are available for individual devices. This means you can have up to 256 unique addresses within that network. Subnet masks are crucial for routing data efficiently, ensuring that information gets to the right destination without getting lost in the digital shuffle. They help devices communicate effectively, making sure that each packet of data knows exactly where to go. Understanding subnet masks is key to mastering networking, making it easier to manage and secure your digital environment. Understanding subnet masks is key to mastering networking, making it easier to manage and secure your digital environment. In the world of networking, understanding broadcast and network addresses is crucial. Picture this. Every subnet has a unique identity. The network address, the first IP in that subnet, acts like the neighborhood signpost, marking the area where all devices reside. It doesn't point to a specific device, rather it identifies the entire subnet itself. Now, let's flip the coin to the broadcast address, which is the last IP in that subnet. This address is like a megaphone, sending messages to every device within that network. When data is sent to the broadcast address, it's like shouting, "Hey everyone, listen up." This allows for efficient communication, especially in scenarios where you want to reach all devices simultaneously. So remember, the network address is your starting point, while broadcast address is your loudspeaker, connecting everyone in the subnet. In the world of networking, understanding broadcast and network addresses is crucial. Picture this. Every subnet has a unique identity. In the world of networking, IP addresses play a crucial role, and they're categorized into classes to streamline address allocation. We have 5 primary classes: A, B, C, D, and E. Class A is like the VIP section, allowing for millions of hosts, perfect for large organizations. Class B is a bit more exclusive, catering to medium-sized networks with thousands of hosts. Class C, on the other hand, is for smaller networks, accommodating up to 254 hosts. Classes D and E, they're the special guests. Class D is reserved for multicast groups, while Class E is for experimental purposes. Understanding these classes helps us manage our networks efficiently, ensuring that every device gets its unique address without a hitch. In the world of networking, IP addresses play a crucial role, and they're categorized into classes to streamline address allocation. Class A addresses are fascinating. They range from 0.0.0.0 to 127.2555, with the first octet falling between 0 and 127. What sets them apart? The first bit is always 0, which means the first octet is dedicated to identifying the network. This allows for a whopping 128 networks, each capable of hosting an astounding 16,777,214 devices. Imagine the scale of a Class A network, perfect for large organizations or even entire countries. The default subnet mask is 255.0.0.0, or at 8 in CDR notation, which means the first 8 bits are for the network, while the remaining 24 bits are reserved for hosts. A prime example of a Class A address is 10.0.0.0. With such vast potential, Class A addresses are the backbone of extensive networking, powering everything from multinational corporations to massive data centers. Class A addresses are fascinating. They range from 0.0.0.0 to 127.2555.2555.255, with the first octet falling between 0 and 127. Class B addresses ranging from 128.0.0 to 191.255.255.255 are essential for medium to large-sized networks. With a default subnet mask of 255.2555.0.0 or 16, they provide a robust structure for managing network traffic. This class supports an impressive 16,184 networks, each capable of hosting up to 65,534 devices. Imagine the connectivity. The first 2 octets are dedicated to the network, while the last 2 are reserved for individual hosts. A prime example is 172.16.0.0, which falls within the private range of 172.16.0.0 to 172.31.255.255, perfect for internal networks. Class B is all about scalability and efficiency, making it a backbone for many organizations. Understanding this class is crucial for network design and management. Class B addresses, ranging from 128.0.0.0 to 191.255.255.255, are essential for medium to large-sized networks. With a default subnet mask of 255.255.0.0 or 16, they provide a robust structure for managing network traffic. Class C addresses ranging from 192.0.0.0 to 223.255.255.255 are essential for small networks like your home or a cozy office. With a default subnet mask of 255.255.255.0 or in 24, they allow 2,097,152 unique networks, each capable of hosting up to 254 devices. Imagine the possibilities. The first 3 octets identify the network, while the last octet is reserved for hosts. A classic example is 192.1168.1.0, a staple in many private networks. Speaking of private ranges, the 192.168.0.0 to 192.168.255.255 range is reserved for internal use, keeping your data safe and sound. Class C addresses are the backbone of small-scale networking, making connectivity simple and efficient. Class C addresses, ranging from 192.0.0.0 to 223.255.255.255, are essential for small networks, like your home or a cozy office. Class D addresses, ranging from 224.0.0.0 to 239.255.2555.255, are the unsung heroes of digital communication. These addresses are specifically reserved for multicast purposes, allowing data to be sent to multiple devices simultaneously. Imagine streaming your favorite show or listening to a live concert with friends, all connected through these special addresses. Unlike regular IP addresses that assign unique identifiers to individual devices, Class D is all about collaboration and efficiency. They play a crucial role in broadcasting and multicasting, ensuring that data flows seamlessly to everyone who needs it. So, the next time you enjoy a live stream or a group video call, remember the Class D addresses quietly working behind the scenes to make it all possible. Class E addresses, ranging from 240.000 to 255.255.255, are a fascinating part of the IP address spectrum. These addresses, with their first octet between 240 and 255, are reserved for future use or experimental purposes. Think of them as the VIP section of the IP world, exclusive and off-limits for general networking. While most of us are busy with classes A, B, and C for everyday internet needs, Class E is set aside for research and development. This means that these addresses could potentially play a crucial role in the evolution of networking technology. So, while they may seem like digital ghosts now, they hold the promise of innovation just waiting to be unlocked. Private IP addresses are essential for internal networks, and they come in three main classes. Class A ranges from 10.0.00 to 10.255.255.255, offering a massive pool of addresses for large organizations. Then we have Class B, which spans 172.16.0.0 to 172.31.255.255, perfect for medium-sized networks. Finally, Class C covers 192.168.0.0, 192.168.255.255, commonly used in home networks. These private ranges are not routable on the public internet, meaning they keep your internal communications secure. To connect to the outside world, we use NAT, or Network Address Translation, which allows multiple devices on a private network to share a single public IP address. This not only conserves IP addresses, but also adds a layer of security. Understanding these ranges is crucial for anyone managing a network, ensuring efficient and secure connectivity. IP routing is like the postal service of the internet, ensuring that data packets find their way from one network to another. Imagine sending a letter. It doesn't go directly to the recipient, but passes through various post offices, each making decisions on the best route. Similarly, routers analyze the destination address of each packet and determine the most efficient path. This process involves complex algorithms and protocols, allowing data to traverse multiple networks seamlessly. Each router acts as a traffic director, managing the flow of information and preventing congestion. Without effective IP routing, our online experiences, streaming videos, browsing websites, or even sending emails would be chaotic and inefficient. It's the backbone of connectivity, enabling everything from social media interactions to critical communications. In essence, IP routing is the unsung hero of the digital world, making sure our data arrives safely and swiftly at its destination. Routing is like being a traffic cop for data. Imagine packets of information zooming around, each with a destination IP address, much like a letter with an address. Routers are the unsung heroes in this digital world, analyzing those addresses and deciding the best path for each packet to take. They look at the network topology, considering factors like speed and congestion, to forward the data to the next hop device or network. It's a complex dance of algorithms and protocols, ensuring that your emails, videos, and web pages reach you swiftly and efficiently. Without routing, the internet would be a chaotic mess, with data lost in transit. So, next time you click send, remember the intricate journey your data takes, guided by the intelligent decisions of routers working tirelessly behind the scenes. Routing is like being a traffic cop for data. Imagine packets of information zooming around, each with a destination IP address, much like a letter with an address. Imagine a bustling city where every building represents a different network. In this city, the router acts like a skilled traffic cop, directing packets of data to their correct destinations. It scans the destination IP addresses, much like reading street signs, and consults its routing table, which is like a detailed map of the city. When a packet arrives, the router quickly determines the best path to take, ensuring that data flows smoothly and efficiently. It's not just about speed. It's about making sure that the right information reaches the right place without getting lost in the chaos. Whether it's streaming your favorite show or sending an email, routers are the unsung heroes of our digital world, tirelessly working behind the scenes to keep us connected. They bridge the gaps between networks, making communication seamless and reliable. So next time you click send or hit play, remember the router, the silent guardian of our online experiences. Imagine a bustling city where every building represents a different network. In this city, the router acts like a skilled traffic cop, directing packets of data to their correct destinations. Imagine a bustling city where every street leads to a different destination. Now, picture a router as the city's traffic cop, guiding data packets to their rightful places. At the heart of this operation is the routing table, a crucial data structure that holds the keys to the network. It's like a map, detailing various destinations and the best paths to reach them. When a packet arrives, the router consults this table, determining the most efficient route based on factors like distance and network conditions. It's a dynamic process. Routes can change, and the table updates in real time, ensuring data flows smoothly. Without this vital tool, packets would be lost in the digital maze, wandering aimlessly. So, next time you send an email or stream a video, remember the unsung hero behind the scenes. The routing table, keeping everything connected and on track. Imagine a bustling city where every street leads to a different destination. Now, picture a router as the city's traffic cop, guiding data packets to their rightful places. Routing protocols Static routing is like setting a course on a map and sticking to it. Once the routes are configured, they remain fixed until someone steps in to make changes. This can be great for smaller networks where everything is predictable, but it can become a hassle if the network evolves or if there's a failure. On the flip side, dynamic routing is like having a GPS that constantly updates based on real-time traffic conditions. Routers communicate with each other using protocols, automatically adjusting their paths to ensure data takes the most efficient route. This adaptability is crucial in larger, more complex networks where changes happen frequently. In essence, static routing offers simplicity and control, while dynamic routing provides flexibility and resilience. Choosing between them depends on your network's needs. Do you prefer stability or adaptability? When I want to send data to another device on a different network, the process kicks off with me preparing a data packet. I include the destination IP address right in the packet header. Next, I send this packet to my local router, known as the default gateway. This router is like traffic cop, examining the destination IP to figure out the best path. It checks its routing table for a match. If it finds one, it forwards the packet to the next hop, which could be another router or even the destination network. If there's no match, it might drop the packet or send it to a default route. This forwarding continues, with each router along the way doing its job until the packet finally reaches the destination network. Once there, it's delivered to the intended device, completing the journey. That's how IP routing works, ensuring my data gets to where it needs to go. Direct routing is a fascinating concept in networking. Imagine you're sending a letter to a neighbor right next door. Instead of going through the postal service, you simply walk it over. That's exactly how direct routing works in a local network. When the source device and the destination device are on the same subnet, the data packet travels directly without needing a router to intervene. This not only speeds up the communication process, but also reduces latency. It's like having a direct line of communication, ensuring that your data reaches its destination quickly and efficiently. So, next time you're streaming a video or sharing files with someone on the same network, remember, that seamless experience is thanks to direct routing, making our digital interactions smoother and faster. Indirect routing is a fascinating process that kicks in when a device needs to communicate with another device on a different network or subnet. Imagine sending a letter to a friend in another city. You can't just drop it in their mailbox. It needs to go through a postal service, right? Similarly, when a data packet is destined for a device outside its local network, it gets forwarded through one or more routers. These routers act like traffic directors, determining the best path for the packet to travel. Each router examines the packet's destination address, making decisions based on its routing table, like a GPS recalculating your route. The packet hops from router to router until it finally reaches its destination. This process ensures that data can traverse vast networks, connecting devices across the globe seamlessly. Indirect routing is essential for the Internet's functionality, enabling everything from streaming videos to sending emails. It's a complex dance of data that keeps our digital world connected. Indirect routing is a fascinating process that kicks in when a device needs to communicate with another device on a different network or subnet. Routing tables are the unsung heroes of network communication. Picture this. Each router has a routing table, a crucial map that guides data packets to their destinations. It starts with the destination network, which is essentially the IP address or range where the data needs to go. Next, we have the next hop, the IP address of the next router that will take the baton and keep the data moving. But it's not just about getting there, it's about how efficiently we get there. That's where the metric comes in. This value indicates the cost of the path. Lower is better. Think of it as the router's way of choosing the fastest route, considering factors like hop count, bandwidth, and delay. Finally, we have the interface, the specific outgoing port on the router that sends the packet on its way. In essence, routing tables are like a GPS for data, ensuring that every packet finds its way home efficiently and effectively. RIP, or Routing Information Protocol, is one of the oldest distance vector protocols still in use today. It's like the classic car of networking, simple, reliable, but a bit limited. RIP uses hop count as its metric, meaning it counts the number of routers a packet must pass through to reach its destination. The maximum hop count is 15, which makes it great for small networks, but a bit of a dinosaur for larger ones. Every 30 seconds, RIP broadcasts its entire routing table to neighboring routers, which can lead to some inefficiencies and slow convergence times. It's not the fastest or the most sophisticated, but its simplicity makes it easy to configure and understand. For small businesses or home networks, RIP can be a solid choice, providing a straightforward way to manage routing without the complexity of more advanced protocols. In a world of rapid technological advancement, RIP reminds us that sometimes simpler solutions can still hold their ground. RIP, or Routing Information Protocol, is one of the oldest distance vector protocols still in use today. It's like the classic car of networking, simple, reliable, but a bit limited. OSPF, or Open Shortest Path First, is a powerful link state protocol designed for larger, more complex networks. Unlike distance vector protocols, OSPF maintains a complete map of the network topology, allowing routers to make informed decisions. It uses Dijkstra's algorithm to calculate the shortest path to each destination, ensuring efficient data routing. Each router shares its link state information with others, creating a synchronized view of the network. This means faster convergence and better scalability. OSPF also supports hierarchical design through areas, which helps manage routing tables and reduces overhead. In essence, OSPF is like a GPS for your network, constantly recalculating the best routes to keep data flowing smoothly. OSPF, or Open Shortest Path First, is a powerful link state protocol designed for larger, more complex networks. Unlike distance vector protocols, OSPF maintains a complete map of the network topology, allowing routers to make informed decisions. Or Enhanced Interior Gateway Routing Protocol is a game changer in the world of networking. It's a Cisco proprietary protocol that brilliantly merges the best features of both distance vector and link state protocols. Imagine having the efficiency of a distance vector protocol, but with the advanced capabilities of link state. That's EIGRP for you. What sets it apart from RIP is its rapid convergence. EIGRP can adapt to network changes almost instantly, minimizing downtime and ensuring smooth data flow. It uses a unique metric based on bandwidth, delay, load, and reliability, allowing for more intelligent routing decisions. Plus, its diffusing update algorithm means that updates are sent only when there's a change, reducing unnecessary traffic. In essence, EIGRP is like having a smart GPS for your network, guiding data packets efficiently and effectively. It's no wonder that many network engineers prefer it for its balance of speed and reliability. EIGRP, or Enhanced Interior Gateway Routing Protocol, is a game changer in the world of networking. It's a Cisco proprietary protocol that brilliantly merges the best features of both distance vector and link state protocols. BGP, or Border Gateway Protocol, is the unsung hero of the internet, silently orchestrating the flow of data between different autonomous systems. Imagine the internet as a vast city with countless neighborhoods, each representing an ISP or network. BGP is the traffic cop, determining the best routes for data packets to travel, ensuring they reach their destination efficiently. It's a complex dance of decision-making, where BGP evaluates multiple paths, considering factors like speed, reliability, and policy. When one route goes down, BGP quickly reroutes traffic, keeping our online experiences smooth and uninterrupted. Without BGP, the internet would be a chaotic mess, with data packets lost in transit. So, the next time you stream a video or send an email, remember the crucial role BGP plays in making it all possible, connecting us across the globe in the blink of an eye. BGP, or Border Gateway Protocol, is the unsung hero of the internet, silently orchestrating the flow of data between different autonomous systems. Routed protocols are the backbone of data communication across networks. Think of them as the postal service for your digital information. They carry data from one point to another, ensuring it reaches the right destination. The most prominent example is the Internet Protocol, or IP. It's like the universal language of networking, addressing and routing packets of data across the vast expanse of the Internet. Then we have IPv6, the successor to IPv4, which expands our address space significantly, accommodating the ever-growing number of devices online. Remember AppleTalk? It was once popular in Apple networks, but it's now a relic of the past. Similarly, IPX, used in Novell NetWare environments, has faded into obscurity. These routed protocols are essential to this communication, allowing devices to connect and share information efficiently. Understanding them is key to grasping how our digital world operates. Routed protocols are the backbone of data communication across networks. Think of them as the postal service for your digital information. They carry data from one point to another, ensuring it reaches the right destination. Routing protocols are the unsung heroes of our networks, enabling routers to communicate and share vital information about network paths. Imagine a bustling city where each router is a traffic officer, directing data packets to their destinations. Take RIP, for instance, one of the oldest protocols, using hop count to find the shortest route, but it can be a bit simplistic. Then there's OSPF, a more sophisticated link state protocol that employs Dijkstra's algorithm, considering link costs to ensure efficient routing. EIGRP, a Cisco favorite, blends the best of both worlds with its hybrid approach, making it versatile and efficient. And let's not forget BGP, the backbone of the Internet, managing routing decisions between different autonomous systems based on policies. Each of these protocols plays a crucial role in keeping our digital world connected and responsive. Routing protocols are the unsung heroes of our networks, enabling routers to communicate and share vital information about network paths. Imagine a bustling city where each router is a traffic officer, directing data packets to their destinations. Administrative the route. Classful routing protocols are like the old school way of managing IP addresses. They don't carry subnet mask information in their updates, relying instead on default masks based on IP address classes A, B, and C. This means they can't handle variable length subnet masking or VLSM, and they don't support classless interdomain routing or CDR. Think of RIPv1 and IGRP. They were the go-to options back in the day, but now they're mostly outdated. On the flip side, we have classless routing protocols, which are modern heroes of networking. They include subnet masks in their updates, allowing for much more flexible IP address allocation. This capability supports VLSM and CIDR, making them scalable and efficient for today's complex networks. Protocols like RIPv2, OSPF, EIGRP, and BGP are the stars of the show now, ensuring that IP address space is utilized effectively. In today's world, classless protocols are the norm, while classful protocols have taken a backseat, rarely seen in contemporary setups. Classful routing protocols are like the old-school way of managing IP addresses. They don't carry subnet mask information in their updates, relying instead on default masks based on IP address classes A, B, and C. First hop redundant calls, or FHRPs, are for maintaining network reliability. Imagine a scenario where your default gateway, the router that directs your traffic outside your local subnet, suddenly fails. Without FHRPs, that could mean downtime and frustration. But with these protocols in place, multiple routers can share the load, ensuring that if one goes down, another seamlessly takes over. This means your network remains operational without any manual intervention. FHR utilize a virtual IP address, which acts as a single point of contact for devices on the network. This virtual IP can shift between based on their status, providing a fault-tolerant environment. In high-availability situations, FHRPs are a game changer, allowing for smooth failover and continuous connectivity. So, when it comes to keeping your network running smoothly, FHRPs are the unsung heroes that ensure your data flows without interruption. First hop redundancy protocols, or FHRPs, are essential for maintaining network reliability. Imagine a scenario where your default gateway, the router that directs your traffic outside your local subnet, suddenly fails. In the world of network, ensuring high availability is crucial, and that's where first hop redundancy protocols, or FHRPs, come into play. Let's dive into the most common ones. First up is HSRP, or Hot Standby Router Protocol, developed by Cisco. It's the go-to choice for many networks. HSRP creates a virtual router, allowing multiple routers to share a single virtual IP address. Picture this. One router, the active router, handles all the traffic, while the standby router sits in the wings, ready to take over if the active one fails. This seamless transition keeps your network running smoothly without interruption. Now imagine if you need load balancing as well. This is where GLBP, or Gateway Load Balancing Protocol, shines. Unlike HSRP, GLBP allows multiple routers to actively share the load, optimizing traffic distribution. And let's not forget VRRP, or Virtual Router Redundancy Protocol, which is an open standard that provides similar functionality to HSRP, ensuring that your network remains resilient. Each of these protocols plays a vital role in maintaining connectivity and reliability in Cisco networks. In the world of networking, ensuring high availability is crucial, and that's where first hop redundancy protocols, or FHRPs, come into play. Let's dive into the most common ones. First up is HSRP, or Hot Standby Router Protocol, developed by Cisco. It's the go-to choice for many networks. In the world of HSRP, or standby routers are in sight. VRRP, or Virtual Router Redundancy Protocol, is a game changer in network reliability. Developed by the IETF, it stands out as an open standard unlike HSRP, which is Cisco proprietary. Imagine a group of routers working together to ensure your gateway is always up and running. In this setup, one router takes the lead as the master, handling all traffic directed to a shared virtual IP address. Meanwhile, the backup routers are on standby, vigilantly monitoring the master. If the master fails, one of the backup routers seamlessly steps in, ensuring uninterrupted service. This dynamic not only enhances redundancy but also boosts network resilience, making VRRP a vital protocol in today's interconnected world. VRRP, or Virtual Router Redundancy Protocol, is a game changer in network reliability. Developed by the IETF, it stands out as an open standard, unlike HSRP, which is Cisco proprietary. GLBP, or Gateway Load Balancing Protocol, is a game in the world of networking. Unlike HSRP and VRRP, which rely on a single active router, GLBP allows multiple routers to share the same virtual IP address while distributing the traffic load.
This means better resource utilization and enhanced performance. Each router in the GLBP group is assigned a unique virtual MAC address, and they work together using a load balancing algorithm. This ensures that no single router is overwhelmed with traffic, allowing for smoother operations and increased reliability.
With GLBP, you get not just redundancy, but true load balancing, making your network more efficient and resilient. GLBP, or Gateway Load Balancing Protocol, is a game changer in the world of networking. Distance vector routing protocol carrying a map. This map is the routing table. It details the distance or cost to various destinations, which can be based on factors like hop count, delay, or bandwidth. The term distance refers to the cost of reaching a destination, where each hop between routers counts as one unit. The vector aspect is all about direction. Routers share their tables with neighbors, revealing not just the distance, but also the next hop to reach each destination. What's really interesting is the periodic updates. Routers regularly exchange their routing tables, allowing them to adapt to changes in the network's topology and recalculate paths as needed. This dynamic process ensures efficient data delivery, making distance vector protocols a vital part of network communication. Distance vector routing protocols are fascinating tools in computer networks, designed to find the best path for data packets. Imagine each router as a traveler carrying a map. This map is the routing table. Quickly and reliably. When a router powers on, it kicks off its journey by initializing its routing table. It knows how to reach itself, but that's about it. As it connects with neighboring routers, it starts sending out periodic updates, sharing its routing table. This is where the magic happens. Each router learns about the distances to other routers and updates its own table. Over time, this exchange of information leads to convergence, where all routers have consistent and accurate routing tables. One of the biggest advantages of distance vector protocols is their simplicity. They're easy to configure, making them ideal for smaller networks. Plus, they require less processing power and memory, which is a win for efficiency. In essence, distance vector protocols are like a friendly neighborhood chat, ensuring everyone knows the best routes to take. When a router powers on, it kicks off its journey by initializing its routing table. It knows how to reach itself, but that's about it. As it connects with neighboring routers, it starts sending out periodic updates, sharing its routing table. Routing Information Protocol version 2, or RIPANG, is a fascinating enhancement of the original RIP designed specifically for IPv6 networks. As a distance vector routing protocol, it efficiently manages how data packets navigate through local and regional networks. What sets RIPing apart is its ability to support the larger address space of IPv6, making it essential for modern networking. It uses a simple metric based on hop count, allowing routers to share information about the best paths to reach various destinations. With a maximum of 15 hops, it ensures that data travels swiftly without overwhelming the network. Plus, RIPing incorporates multicast for updates, reducing unnecessary traffic. This makes it not just a protocol, but a vital tool for seamless communication in today's interconnected world. Routing Information Protocol version 2, or RIPANG, is a fascinating enhancement of the original RIP, designed specifically for IPv6 networks. As a distance vector routing protocol, it efficiently manages how data packets navigate through local and regional networks. RIPANG, or Routing Information Protocol Next Generation, is all about simplicity in routing. It uses hop count as its metric, which means it counts the number of steps a packet takes to reach its destination. The catch? The maximum hop count is 15. If a destination is more than 15 hops away, it's deemed unreachable. This limitation makes RIPing ideal for smaller to medium-sized networks, where quick and efficient routing is key. However, in larger networks, that 15-hop ceiling can feel a bit restrictive. It's like trying to fit a square peg in a round hole. So, while RIPing keeps things straightforward, it's essential to consider your network size when choosing your routing protocol. RIPing is a fascinating evolution in the world of networking, specifically designed for IPv6. Unlike its predecessors, RIPv1 and RIPv2, which cater to the older IPv4 networks, RIPing embraces the vastness of IPv6. Imagine a world where the address space is exponentially larger, accommodating the ever-growing number of devices. With RIPing, routers can seamlessly share routing information, ensuring efficient communication across this expansive network. It introduces a new format for routing table entries, perfectly tailored for IPv6 addresses. This means more flexibility and better performance in routing, allowing networks to scale without the limitations we faced with IPv4. In a nutshell, RIPing is not just a protocol. It's a crucial step towards a more connected future. RIPing is a fascinating evolution in the world of networking, specifically designed for IPv6. Unlike its predecessors, RIPv1 and RIPv2, which cater to the older IPv4 networks, RIPing embraces the vastness of IPv6. In the world of networking, the distance vector algorithm is like a well-choreographed dance between routers. Take RIPing, for instance. Each router holds a routing table, a treasure map of sorts, detailing the best paths to reach various destinations. But here's the twist. Instead of keeping this information to themselves, routers share their tables with their neighbors. Every so often, they engage in a friendly exchange, updating each other on latest routes and distances. Imagine routers chatting over coffee saying, "Hey, I found a quicker route to that destination." This constant communication helps each router refine its own table, ensuring that data packets take the most efficient paths. However, it's not just about sharing, it's about learning and adapting. If one router discovers a better route or a blockage, it spreads that knowledge, allowing the entire network to evolve. The collaborative effort keeps the network dynamic and responsive, making sure that no matter the changes, data flows smoothly. That's the beauty of the distance vector algorithm in action.
Every 30 seconds, RIPNG routers spring into action, sending out routing updates that are crucial for keeping our networks running smoothly. These updates are like a friendly neighborhood gossip session, where routers share the latest routing information about destinations within the network.
Imagine each router as a messenger, delivering news to its neighbors about new routes or changes to existing ones. This constant communication ensures that every router stays informed and can make the best decisions for data traffic. It's a dynamic dance of information where every second counts, and staying updated is key to efficient routing. So, next time you think about your network, remember the vital role these periodic updates play in keeping everything connected and efficient. Every 30 seconds, RIPing routers spring into action, sending out routing updates that are crucial for keeping our networks running smoothly. RIPing revolutionizes routing by embracing classless interdomain routing, or CIDR. Unlike its predecessor, RIPv1, which was stuck in the rigid world of classful addressing, RIPing allows for subnet masks of varying lengths. This flexibility means we can efficiently utilize IP address space, accommodating networks of all sizes. Imagine a network that can seamlessly adapt to your needs, whether you're managing a small office or a sprawling enterprise. With RIPing, routing becomes smarter and more efficient, reducing waste and optimizing performance. It's a game changer in the world of networking. RIPing revolutionizes routing by embracing classless interdomain routing, or CADR. Unlike its predecessor, RIPv1, which was stuck in the rigid world of classful addressing, RIPing allows for subnet masks of varying lengths. This flexibility means we can efficiently utilize IP address space, accommodating networks of all sizes. RIPing, or Routing Information Protocol Next Generation, is a breath of fresh air for network administrators. Its straightforward configuration process sets it apart from more complex protocols like OSPF or EIGRP. With RIPing, you can set up routing in just a few simple commands, making it perfect for small or less complex networks. Imagine having a routing protocol that doesn't require a PhD to configure. It uses a distance vector algorithm, which means it shares routing information based on hop count. This simplicity means less room for error and quicker troubleshooting. While it may not have the advanced features of its counterparts, its ease of use is why many still rely on RIPing. In a world where complexity often reigns, RIPing stands out as a reliable, user-friendly choice for those who need efficient routing without the headache. RIPing, or Routing Information Protocol Next Generation, is a breath of fresh air for network administrators. Its straightforward configuration process sets it apart from more complex protocols like OSPF or EIGRP. In the world of networking, every router using RIPing has a crucial role to play, and it all starts with the routing table. Picture this. Each entry in the table is like a treasure map, guiding us to different destinations across the vast landscape of IPv6 networks. For every destination, we store the IPv6 address, a unique identifier that tells us exactly where to go. But it doesn't stop there. We also keep track of the next hop router, the trusty guide that leads us on a journey. The hop count, or metric, is like a scorecard, showing how many steps we need to take to reach our goal. And to ensure we're on the right path, we log the time of the last update, helping us determine if our route is still valid. This dynamic system ensures efficient communication, allowing data to flow seamlessly across networks. It's all about making connections and keeping the information fresh, so we can navigate the digital world with confidence. Every 30 seconds, routers engage in a vital dance of communication, exchanging their routing tables with direct neighbors using RIPing multicast messages. This happens on the special address FF02.9, where the magic of networking unfolds. Each update is like a snapshot of the router's current knowledge, revealing the best paths to reach various destinations. If a router hears about a route with a lower hop count from a neighbor, it eagerly updates its own table, optimizing its path for efficiency. This constant flow of information ensures that the network remains agile and responsive, adapting to changes and finding the quickest routes. It's a fascinating interplay of collaboration and competition, all happening in the blink of an eye, keeping our data flowing smoothly across the vast expanse of the internet. Every 30 seconds, routers engage in a vital dance of communication, exchanging their routing tables with direct neighbors using RIPing multicast messages. This happens on the special address FF02.9, where the magic of networking unfolds. Convergence is a fascinating yet crucial process in networking. Imagine a bustling city where traffic lights need to adjust after a road closure. Similarly, when a router detects a change, like a link failure or a new router joining the network, it must communicate with its peers to update routing tables. This process ensures that all routers have consistent information, but it doesn't happen instantly. Take RIPing, for instance. In large networks, its slow convergence time can lead to routing loops or delays in packet delivery. Picture packets caught in a loop, endlessly circling, while your data waits impatiently. Efficient convergence is essential for a seamless network experience, ensuring that our digital highways remain clear and traffic flows smoothly. Convergence is a fascinating yet crucial process in networking. Imagine a bustling city where traffic lights need to adjust after a road closure. Routing loops can be a real headache in distance vector protocols like RIPing. Imagine two routers caught in a never-ending game of ping pong, sending packets back and forth endlessly because of outdated routing info. To combat this chaos, RIPing employs some clever strategies. First up is split horizon. This means a router won't send routing information back to the router it earned it from, effectively cutting off the loop at its source. Then we have poison reverse. If a router discovers a route is unreachable, it advertises that route as having an infinite distance, 16 hops in RIPing terms, essentially saying, don't even think about it. And let's not forget about hold-down timers. When a router learns of a route failure, it goes into a hold-down state, ignoring any new routing info about that route for a set period. This gives the network time to stabilize and prevents incorrect information from spreading. These mechanisms work together to keep our networks running smoothly, avoiding the pitfalls of routing loops. In the world of ping, route aging plays a crucial role in maintaining the integrity of our routing tables. Picture this. A route remains valid as long as it receives periodic updates. But what happens if a router goes silent? After 180 seconds without an update, that route is considered to have aged out. This mechanism is essential. It prevents stale or incorrect routes from cluttering our tables, ensuring that data flows efficiently across the network. Think of it as a digital housekeeping routine, keeping our pathways clear and our connections reliable. By regularly refreshing routes, we can adapt to changes in the network landscape, making sure our data always take the best path. In essence, route aging is the unsung hero of network reliability, keeping everything running smoothly. RIPing, or Routing Information Protocol Next Generation, is a crucial player in the world of IPv6 networking. It operates over UDP on port 521, ensuring efficient communication. Each RIPing message is structured with several key fields. First, the command field tells us whether it's a request or response. Then, we have the version field, which is always set to 2 for RIPing. Next up is the reserved field, kept for future enhancements. The entry count follows, indicating how many routing table entries are included in the message. Now, let's dive into the routing entries. Each entry contains a destination IPv6 address, pinpointing the target network. The metric reveals the number of hops needed to reach that destination, while the next hop field specifies the next router to forward the packet. This streamlined format makes RIPing an efficient choice for managing routing information in modern networks. RIPing, or Routing Information Protocol Next Generation, is a crucial player in the world of IPv6 networking. It operates over UDP on port 521, ensuring efficient communication. Each RIPing message is structured with several key fields. RIPing offers some compelling advantages that make it a go-to choice for many network administrators. First off, its simplicity is a game changer. Configuring RIPing is straightforward, so you don't need to be a routing protocol expert to get it up and running. Then there's the IPv6 support. As networks evolve, so does the need for protocols that can handle modern addressing. RIPing is built for IPv6, ensuring that your network is future-proof and ready for the next generation of internet connectivity. And let's not forget about classless routing. Unlike its predecessor RIPv1, RIPing embraces CIDR and variable length subnet masks. This flexibility allows you to design subnets that fit your needs perfectly, optimizing your network's performance. In a nutshell, RIPing combines ease of use with robust features, making it an excellent choice for today's networks. Are replicable disadvantages that can really impact network performance. First off, its slow convergence is a significant drawback. When changes occur, RIPing takes its sweet time to adapt, unlike OSPF or EIGRP, which are much quicker on their feet. Then there's the issue of scalability. With a strict 15-hop limit, RIPing is really only cut out for small to medium-sized networks. If you're dealing with a larger setup, you're going to hit a wall pretty. Routing loops are another concern. While techniques like split horizon and poison reverse help, they don't completely eliminate the risk, especially in complex networks. Finally, RIPing lacks advanced features that modern protocols offer, such as authentication, hierarchical routing, and route summarization. These features are essential for efficient and secure routing in today's networks. Overall, while RIPing has its place, it's clear that it falls short in several critical areas. RIPing has some notable disadvantages that can really impact network performance. First off, its slow convergence is a significant drawback. Open Short Path First, or OSPF, is a house in the world of dynamic routing protocols. Imagine a bustling city where every intersection is a router, and OSPF is the traffic manager, ensuring data packets find the quickest route through a complex network. Unlike distance vector protocols, OSPF is a link state protocol, which means it builds a detailed map of the entire network topology. This allows it to make smart, informed decisions about the best paths for data to travel. When a change occurs, like a road closure or a new route opening, OSPF quickly updates its map, ensuring that data packets are always taking the most efficient route. This adaptability is crucial in large networks, where efficiency can make or break performance. With OSPF, we're not just routing data, we're optimizing the entire flow of information, making it one of the most trusted protocols in IP networking today. Router type. OSPF categorizes routers into different types. Internal router, IR, is a router whose interfaces are all within the same area. Area border router, ABR, is a router that connects two or more OSPF areas. Backbone router refers to routers that belong to the backbone area, known as Area 0. Autonomous System Boundary Router, ASBR, is a router that connects an OSPF domain to an external network, such as another AS or the Internet. OSPF divides large networks into smaller logical segments called areas. The backbone area, or Area 0, is the core of an OSPF network, and all other areas must be connected to it. OSPF allows networks to be structured hierarchically. Instead of having a flat routing structure, OSPF divides the network into areas. This reduces routing overhead and improves scalability. The central area in OSPF is Area 0, also known as the backbone area. All other areas must Area 0. Non-backbone areas connect to Area 0 via ABRs, helping to organize the network into manageable sections. Each router in an OSPF network maintains a routing table that holds the best to reach different destinations. This table is built using the information in the LSDB. OSPF routers exchange LSAs to share information about their directly connected links and the state of those links. Type 1 LSA, also known as router LSA, is generated by each router to describe its own links and the status of those links. Type 2 LSA, or network LSA, is generated by a designated router to describe network segment and its attached routers. Type 3 LSA, referred to as summary LSA, is generated by ABRs to summarize network information between areas. Type 4 LSA, known as ASBR summary LSA, is generated by ABRs to describe the route to an ASBR. Finally, Type 5 LSA, or external LSA, is generated by ASBRs to describe routes to destinations outside the OSPF domain. OSPF routers exchange LSAs to share information about their directly connected links and the state of those links. Type 1 LSA, also known as router LSA, is generated by each router to describe its own links and the status of those links. Type 2 LSA, or network LSA, is generated by a designated router to describe a network segment and its attached routers. Hello Protocol and Neighbor Establishment. OSPF routers use hello packets to discover neighbors and establish relationships. Routers on the same link send hello packets to identify each other and agree on certain parameters such as router IDs, hello and dead intervals, area ID, and authentication method. Once a router receives a hello packet from another router, they establish a neighbor relationship. This relationship is the basis for exchanging link state information. Hello packets are essential for maintaining the OSPF network and ensuring that routers can communicate effectively with one another. Hello protocol and neighbor establishment. OSPF routers use hello packets to discover neighbors and establish relationships. Routers on the same link send hello packets to identify each other and agree on certain parameters such as router IDs, hello and dead intervals, area ID, and authentication method. In OSPF, the link state database, or LSDB, is the backbone of network synchronization. Imagine each router as a storyteller, sharing the same tale of the network's topology. When a change occurs, like a new link or a router going down, each router floods the area with updates, ensuring that every storyteller has the latest version of the story. This synchronization is crucial. It prevents discrepancies that could lead to routing loops or black holes. By maintaining a consistent LSDB, OSPF routers can calculate the shortest path to each destination using Dijkstra's algorithm. This means efficient routing and optimal performance. In essence, the LSDB is the glue that holds the OSPF network together, creating a seamless, reliable, communicable communication environment. In OSPF, the link state database, or LSDB, is the backbone of network synchronization. Imagine each router as a storyteller, sharing the same tale of the network's topology. Once the LSDB is complete, each router runs the SPF algorithm based on Dijkstra's algorithm to calculate the shortest path tree, SPD. The SPF algorithm uses the LSD to calculate the shortest, best path to each destination in the network. The result of the SPF calculation is a routing table, which contains the best routes to all reachable destinations. Once the LSDB is complete, each router runs the SPF algorithm, based on Dijkstra's algorithm, to calculate the short path tree, SPT. In OSPF, we have three main types of routes that keep our networks running smoothly. First, we have intra-area routes. These are the routes that exist within the same area, allowing for efficient communication among devices. Then we move to inter-area routes, which connect different areas within the OSPF domain. These routes are exchanged through area border routers, or ABRs, ensuring that information flows seamlessly between areas. Finally, we have external routes, which are crucial for reaching destinations outside the OSPF domain. These routes are injected into OSPF by Autonomous System Boundary Routers, or ASBRs, using Type 5 LSAs. Understanding these route types is essential for optimizing OSPF performance and ensuring reliable connectivity across diverse networks. OSPF, or Open Shortest Path First, is a powerhouse in routing protocols, and its features are designed to enhance network security and efficiency. First off, authentication is key. OSPF ensures that only authorized routers can join the network, using either plain text or the more secure MD5 hashing. This keeps unwanted guests out. Then there's route summarization, which is a game changer. By summarizing routes at area boundaries, OSPF reduces the size of routing tables and link state databases, making the network more manageable. Load balancing is another fantastic feature. OSPF supports equal cost multipath routing, allowing multiple best paths to be utilized simultaneously, which optimizes bandwidth usage. Lastly, OSPF's area design promotes scalability. The backbone area, known as Area 0, centralizes routing information, while non-backbone areas help minimize overhead. This hierarchical structure is what makes OSPF so effective in large networks. OSPF uses several timers to control how quickly routers react to changes in the network. The hello timer is the interval between hello packets sent by a router to its neighbors, typically 10 seconds on LAN. The dead timer is the time a router will wait for a hello packet before declaring neighbor down, typically 40 seconds on a LAN. The retransmission timer is the interval at which a router retransmits an LSR, or link state request, if no acknowledgement is received. OSPF uses several timers to control how quickly routers react to changes in the network. The hello timer is the interval between hello packets sent by router to its neighbors, typically 10 seconds on a LAN. The backbone area, also known as Area 0, is the core of the OSPF network, where the inter-area routing occurs. All areas must connect to Area 0. The stub area is a simplified area where external routes are not propagated, and only a default route is available for external destinations. The totally stubby area is a more restrictive version of a stub area, where not only external routes but also summary routes are not propagated. Finally, the NSSA, or not-so-stubby area, is a hybrid area that allows limited external routes to be introduced while minimizing the flooding of external LSAs. EIGRP, or Enhanced Interior Gateway Routing Protocol, is a game changer in the world of networking. Imagine a protocol that combines the best of distance vector and link state routing. That's EIGRP for you. Developed by Cisco, it builds on the original IGRP, addressing its limitations while introducing features like rapid convergence and support for multiple network layer protocols. What sets EIGRP apart is its use of the diffusing update algorithm, which allows for efficient routing updates and minimized bandwidth usage. It also employs a metric based on bandwidth, delay, load, and reliability, ensuring that the best path is chosen dynamically. With EIGRP, you get fast, scalable, and reliable routing within an autonomous system, making it a favorite among network engineers. It's like having a smart GPS for your data packets, always finding the quickest route to their destination. EIGRP, or Enhanced Interior Gateway Routing Protocol, is a game changer in the world of networking. Imagine a protocol that combines the best of distance vector and link state routing. That's EIGRP for you. IGRP, or Enhanced Interior Gateway Routing Protocol, is fascinating because it's a hybrid protocol that cleverly blends the best of distance vector and link state protocols. Imagine a neighborhood where routers are like friendly neighbors, sharing their knowledge only with those right next door. That's the distance vector aspect. IGRP exchanges routing information directly with its neighbors, keeping things efficient and localized. But it doesn't stop there. EIGRP also incorporates link state features, allowing it to maintain a more comprehensive view of the network. This means it can quickly adapt to changes, ensuring optimal routing paths. So, while it communicates like a distance vector protocol, it possesses the intelligence and adaptability of link state protocols, making it a powerful tool in modern networking. In the world of networking, EIGRP stands out with its link state characteristics. Unlike traditional distance vector protocols, EIGRP employs a more efficient algorithm for determining the best path. This means faster convergence and less bandwidth consumption. Each router maintains a complete view of the network topology, allowing for smarter routing decisions. Imagine a team where everyone knows the entire field, no more guesswork or outdated information. This holistic perspective not only enhances reliability, but also optimizes performance. With EIGRP, routers communicate their state and share updates, ensuring that every device is on the same page. It's like having a GPS that not only shows your route, but also updates in real time based on traffic conditions. This is the future of routing: intelligent, efficient, and ready for the demands of modern networks. In the world of networking, the diffusing update algorithm, or DUAL, is a game changer for EIGRP. Imagine navigating a complex city with multiple routes. DUAL helps us find the best path to our destination while keeping us safe from traffic jams, also known as routing loops. It does this by maintaining two key players: the successor, which is our primary route, and the feasible successor, our backup.
If the successor fails, the feasible successor steps in seamlessly, ensuring that our data packets keep flowing without interruption. This dual path strategy not only enhances reliability, but also optimizes network performance. With Dual, EIGRP stands out as a robust protocol, making sure our networks are efficient and loop-free.
In the world of networking, the diffusing update algorithm, or DUAL, is a game changer for EIGRP. Imagine navigating a complex city with multiple routes. DUAL helps us find the best path to our destination while keeping us safe from traffic jams, also known as routing loops. It does this by maintaining two key players: the successor, which is our primary route, and the feasible successor, our backup. EIGRP, or Enhanced Interior Gateway Routing Protocol, is a powerhouse when it comes to supporting multiple network layer protocols. It's like the Swiss Army knife of routing. While it can handle IPv4, IPv6, AppleTalk, and even IPX, its real strength shines with IPv4 and IPv6. Imagine a network that seamlessly adapts to both legacy and modern systems. EIGRP makes that possible. It uses a unique distance vector algorithm, which means it can quickly find the best path for data, reducing latency and improving efficiency. Plus, its support for unequal cost load balancing allows for optimized bandwidth usage. EIGRP isn't just versatile, it's smart, making it a top choice for dynamic networks. So, whether you're managing a small office or a sprawling enterprise, EIGRP has got your back, ensuring smooth communication across diverse protocols. EIGRP, or Enhanced Interior Gateway Routing Protocol, is a powerhouse when it comes to supporting multiple network layer protocols.
EIGRP is a game changer when it comes to network convergence. Unlike traditional distance vector protocols like RIP, which can take ages to update, EIGRP uses the diffusing update algorithm, or DUAL. This means it can quickly determine the best paths and react to changes almost instantly.
What really sets EIGRP apart is its use of incremental updates. Instead of bombarding the network with complete routing tables every time there's a change, EIGRP only sends the updates that matter, the changes. This not only reduces bandwidth usage, but also speeds up the convergence process significantly. Imagine a network that adapts in real time, minimizing downtime and maximizing efficiency. That's the power of EIGRP. It's like having a smart assistant that knows exactly what's happening and responds in a flash, keeping your network running smoothly and reliably. EIGRP, or Enhanced Interior Gateway Routing Protocol, is a powerhouse when it comes to scalability in larger networks. Unlike link state protocols like OSPF, which can become resource hungry as the network grows, EIGRP is designed to be efficient and lightweight. It uses a hybrid approach, combining the best of distance vector and link state. So, if you're looking for a routing protocol that can grow with your needs without draining your resources, EIGRP is the clear choice. EIGRP, or Enhanced Interior Gateway Routing Protocol, is a powerhouse when it comes to scalability in larger networks. EIGRP neighbors are like the best friends of routers, sharing vital routing information to keep our networks running smoothly. It all starts with those friendly hello packets. When two routers meet, they exchange these packets to say, "Hey, I'm here." This initiates a relationship, allowing them to share their routing tables and learn about the best paths for data. Once they establish this bond, they can quickly adapt to changes in the network, ensuring efficient data flow. It's a dynamic partnership that enhances redundancy and optimizes performance. So, next time you think about EIGRP, remember, it's all about those connections and the seamless communication that keeps our digital world connected. EIGRP neighbors are like the best friends of routers, sharing vital routing information to keep our networks running smoothly. It all starts with those friendly hello packets. When two routers meet, they exchange these packets to say, "Hey, I'm here." This initiates a relationship, allowing them to share their routing tables and learn about the best paths for data. Hello packets play a crucial role in the world of EIGRP routers. These little data packets are like friendly waves between neighbors, ensuring that connections remain strong and reliable. Every few seconds, each router sends out a hello packet, checking in to confirm that its neighbors are still present and responsive. This process not only helps in discovering new neighbors, but also maintains the existing relationships. If a router doesn't receive a hello packet from a neighbor within a certain time frame, it assumes something's gone wrong and can take action to reroute traffic. It's a simple yet effective way to keep the network healthy and efficient, ensuring data flows smoothly without interruptions. So, next time you think about EIGRP, remember the vital role these hello packets play in keeping our networks connected and thriving. Hello packets play a crucial role in the world of EIGRP routers. These little data packets are like friendly waves between neighbors, ensuring that connections remain strong and reliable. In the world of EIGRP, each router is like a meticulous librarian, maintaining a topology table that catalogs all the routes it learns from its neighbors. This table is crucial. It holds not just the primary routes, known as successors, but also the backup routes, or feasible successors. Think of successors as the main characters in a story, guiding data packets along the best path. Meanwhile, feasible successors are the reliable sidekicks, ready to step in if the primary route fails. This dual route strategy ensures that data flows smoothly, even in the face of network changes. By constantly updating this topology table, routers can quickly adapt, making EIGRP one of the most efficient routing protocols out there. It's all about resilience and efficiency in the ever-evolving landscape of networking. The EIGRP routing table is a fascinating aspect of how networks communicate efficiently. It stores the best routes, known as successor routes, determined by the dual algorithm. This algorithm is like a smart decision maker, evaluating multiple paths and selecting the most optimal one based on metrics like bandwidth, delay, and reliability. What's interesting is that EIGRP doesn't just stop at the best route, it also keeps track of feasible successors. These are backup routes that can be quickly activated if the primary path fails, ensuring minimal downtime. The routing table is dynamic, constantly updating as network conditions change, which allows for rapid adaptation to new topologies. In essence, the EIGRP routing table is a critical component that ensures data packets find their way through the network efficiently, making it a cornerstone of reliable communication in modern networking. Understanding this process not only enhances our grasp of EIGRP, but also highlights the elegance of network design. In the world of EIGRP, the feasible successor plays a crucial role in ensuring network reliability. Think of it as your backup plan, ready to jump in if the primary route or successor fails. But not just any route can qualify, it must meet the feasibility condition. This means its reported distance must be less than the feasible distance of the current successor. If it checks out, it's immediately available for use, allowing for seamless traffic flow without the need for recalculating routes. This efficiency is what makes EIGRP so robust. So the next time you configure your network, remember the importance of feasible successors. They're your safety net in the dynamic world of routing. EIGRP's dual or diffusing update algorithm is a game changer in the world of routing. Imagine a highway system where every route is constantly monitored for traffic. That's what dual does. It ensures loop-free routing by keeping a close eye on the best paths. When a primary route fails, dual doesn't just leave you stranded, it has a backup plan in place, known as the feasible successor. This means your data can reroute seamlessly, maintaining efficiency and reliability. Dual uses a metric called the feasible distance to evaluate routes, ensuring that the best paths are always at your fingertips. It's like having a GPS that not only finds the quickest route, but also remembers alternate paths, keeping your network running smoothly and efficiently. EIGRP's dual, or diffusing update algorithm, is a game changer in the world of routing. Imagine a highway system where every route is constantly monitored for traffic. IGRP, or Enhanced Interior Gateway, routing protocol uses a composite metric to determine the best path for data packets. This metric is a blend of several key factors. First up is bandwidth, which measures the speed of the link in kilobits per second. The higher the bandwidth, the better. Next is delay, the time it takes for a packet to travel across the link, measured in microseconds. Lower delay means faster delivery.
Then we have load, which reflects how much of the link's capacity is being used. While not always factored in, it can impact performance. Reliability is another crucial element. Assessing the link stability, again, not always in play by default. Finally, there's MTU, or Maximum Transmission Unit, which defines the largest packet size that can be sent. All these factors work together to ensure EIGRP finds the most efficient route for your data.
Optimizing network performance like a pro. EIGRP uses these metrics to make informed decisions about routing. Understanding these components is essential for anyone looking to enhance their network's efficiency and reliability. When EIGRP routers establish a neighbor relationship, they kick off an efficient exchange of routing information. Initially, they share their entire routing tables, which is known as a full table update. It's like giving your friend a complete list of everything in your pantry. But here's where EIGRP shines. After that first exchange, it only sends incremental updates. Imagine only telling your friend about the new snacks you bought, instead of rehashing the entire pantry list every time. This method conserves bandwidth and reduces processing time, making EIGRP far more efficient than protocols like RIP, which send complete updates regularly. By focusing on changes, EIGRP ensures that routers stay synchronized without overwhelming the network. It's a smart, streamlined approach to routing that keeps everything running smoothly. When routers receive updates, they dive into the dual algorithm, a critical process for determining the best path, known as the successor, to each destination. Dual operates on a simple yet powerful principle. It ensures that only the most efficient path is utilized for data transmission. But it doesn't stop there. It also keeps backup routes, called feasible successors, ready to step in if the primary path fails. This dual approach not only enhances network reliability, but also optimizes performance. By continuously evaluating and updating these paths, Dual maintains a dynamic routing environment, ensuring that data flows smoothly and efficiently across the network. It's like having a GPS that not only finds the fastest route, but also remembers alternative paths just in case. When routers receive updates, they dive into the dual algorithm, a critical process for determining the best path, known as the successor to each destination. EIGRP is like a vigilant guardian of your network routes. It constantly monitors the status of each route, ensuring everything runs smoothly. When a route fails, EIGRP doesn't just sit back and wait, it springs into action. Within seconds, it identifies a feasible successor, a backup route that can take over seamlessly. This quick switch not only keeps your data flowing, but also prevents those pesky routing loops that can disrupt communication. It's all about efficiency and reliability. With EIGRP, you can trust that your network is always one step ahead, ready to adapt and keep your connection strong. EIGRP, or Enhanced Interior Gateway Routing Protocol, communicates using several essential packet types that keep networks running smoothly. First up, we have the Hello packet. This little guy is crucial for establishing and maintaining neighbor relationships, ensuring routers can chat with each other. Then there's the Update packet, which is like the gossip of the network, sharing routing information with neighbors. EIGRP is efficient, sending only partial updates so it doesn't overwhelm the network. When a router needs to ask about a route, it sends out a query packet. This is especially handy when a route goes down and needs a replacement. In response, we have the Reply packet, which delivers the requested routing information back to the querying router. Lastly, there's the ACK packet. a simple yet vital component that acknowledges the receipt of any EIGRP packet, ensuring everything is accounted for. Each of these packets plays a critical role in maintaining a robust and efficient routing environment. EIGRP is a game changer in the world of networking. First off, let's talk about faster convergence. Thanks to DUAL, EIGRP can adapt quickly, leaving distance vector protocols like RIP in the dust. This means less downtime and a more reliable network. Then there's scalability. EIGRP shines in large networks, efficiently managing routes without breaking a sweat. It's like having a well-trained team that can handle any challenge, no matter the size. And let's not forget about bandwidth. EIGRP sends only incremental updates, which means it conserves bandwidth like a pro. No more flooding the network with full routing tables, just the essentials. Finally, Dual ensures loop-free routing, which is crucial for maintaining stability. With EIGRP, you get a robust, efficient, and reliable routing protocol that keeps your network running smoothly. EIGRP, while powerful, does come with its share of disadvantages. First off, it started as a Cisco proprietary protocol. This means that for a long time you were pretty much locked into the Cisco ecosystem if you wanted to use it. Sure, some versions have been open source, but that initial exclusivity can be a deal breaker for many. Then there's the complexity of configuration. Now don't get me wrong, EIGRP is definitely easier to set up than OSPF, but it still demands a careful touch. You can't just throw it on your network and hope for the best. You need a solid design and a keen understanding of how it works to avoid potential pitfalls. So, while EIGRP has its perks, it's not without its challenges. EIGRP, while powerful, does come with its share of disadvantages. First off, it started as a Cisco proprietary protocol. This means that for a long time, you were pretty much locked into the Cisco ecosystem if you wanted to use it. Access control lists, or ACLs, are the unsung heroes of network security. Imagine them as the gatekeepers of your digital fortress, meticulously deciding who gets in and who stays out. Every packet of data that tries to enter or leave your network is scrutinized against a set of predefined rules. This means that unauthorized access is denied, while legitimate traffic flows smoothly. ACLs are vital for enforcing security policies, ensuring that only the right users and devices can access sensitive resources. They help manage network traffic, preventing congestion and potential attacks. Whether it's a router or a firewall, ACLs are everywhere, working tirelessly to protect your network from threats. So, the next time you connect to the internet, remember that behind the scenes, ACLs are hard at work, keeping your data safe and sound. Access control lists, or ACLs, are essential tools in network routers that serve multiple purposes. First, they allow us to fine-tune traffic filtering, enabling or blocking specific types of data based on criteria like source or destination IP addresses, protocols, or ports. This precision is crucial for maintaining security. By blocking malicious traffic, we prevent unauthorized access to our networks. But it doesn't stop there. ACLs also enhance network performance by filtering out unnecessary packets, ensuring that only relevant data flows through. This not only speeds up our systems, but also optimizes bandwidth usage. Moreover, ACLs help enforce compliance with organizational and regulatory policies, controlling access to sensitive resources. By managing who can access what, we protect our data and maintain integrity. In a world where cybersecurity threats are ever present, ACLs are our frontline defense, balancing accessibility with security and efficiency. Standard Access Control Lists, or ACLs, are a fundamental tool in network security. They filter traffic based solely on the source IP address, making them less granular but incredibly straightforward to configure. Imagine you want to allow or deny traffic from a specific IP. It's as simple as that. With a standard ACL, you can easily manage who gets in and who stays out. For instance, if you want to block a rogue device from accessing your network, just specify its IP address. And voila! You've tightened your security without the complexity of more advanced filtering options. While they lack the detailed control of extended ACLs, their simplicity is their strength. Perfect for quick setups or smaller networks, standard ACLs help you maintain a clean and efficient traffic flow. So, when you need a straightforward solution to manage access, remember the power of standard ACLs. They keep your network secure without the fuss. Standard Access Control Lists, or ACLs, are a fundamental tool in network security. They filter traffic based solely on the source IP address, making them less granular but incredibly straightforward to configure. Extended ACLs are a powerful tool in network security, allowing us to filter traffic with precision. Imagine being able to control not just who can access your network, but how they do it. With extended ACLs, we can specify source and destination IP addresses, ensuring that only the right devices communicate. But it doesn't stop there. We can also filter by protocol, whether it's TCP, UDP, or ICMP, tailoring our rules to the exact needs of our network. And let's not forget about port numbers. Want to allow HTTP traffic while blocking FTP? No problem. Extended ACLs give us that level of granularity and flexibility that standard ACLs simply can't match. This means enhanced security and better performance as we can fine-tune our traffic flow. In a world where every packet counts, extended ACLs are the key to a robust and efficient network. Named ACLs are a game changer in network management. Unlike standard or extended ACLs that rely on numbers, named ACLs use descriptive names, making it much easier to identify and manage rules, especially in large configurations. Imagine trying to remember what ACL 101 does versus a name like HR traffic restriction. It's a no-brainer. With named ACLs, you can quickly understand the purpose of each rule at a glance, reducing the chances of errors during configuration changes. Plus, they allow for more flexibility. You can modify rules without having to rewrite the entire list, saving time and effort. In complex networks, clarity is key, and named ACLs provide that clarity. They streamline the process, making it simpler to enforce security policies and manage traffic flow. In short, named ACLs are not just a convenience, they're essential for efficient network management. Dynamic ACLs are a game changer in network security, allowing for temporary access based on user authentication. Imagine you're a remote worker needing to access sensitive data. With dynamic ACLs, you can authenticate your identity, and voila, you gain access only for the duration you need. This means enhanced security, as permissions are granted on the fly and revoked automatically when you're done. It's like having a VIP pass that expires after your concert ends. No lingering access, just the right amount of control. This approach is particularly useful in remote access scenarios, where flexibility and security must. Dynamic ACLs are a game changer in network security, allowing for temporary access based on user authentication. Imagine you're a remote worker needing to access sensitive data. With dynamic ACLs, you can authenticate your identity, and voila, you gain access only for the duration you need. Reflexive ACLs are a game changer in network security. Imagine a system that automatically creates temporary rules to allow return traffic for established sessions. It's like having a smart bouncer at a club, only letting in the right people and ensuring they can get back in after stepping out. This dynamic approach enhances security by permitting only legitimate traffic, reducing the risk of unauthorized access. When a session is initiated, the reflexive ACL kicks in, creating a pathway for the response traffic, while keeping everything else locked down. It's efficient, it's secure, and it means you can focus on your work without worrying about unwanted intrusions. With reflexive ACLs, your network is not just protected, it's intelligently managed. Time-based ACLs are a game changer for network management. Imagine having the power to control internet access based on the clock. Picture this. It's 9 a.m. and your team is diving into work. With a time-based ACL, you can automatically block social media traffic during these crucial hours. No more distractions. As the clock strikes noon, you can lift those restrictions, allowing employees to take a well-deserved break and catch up on their feeds. This not only boosts productivity, but also helps maintain a healthy work-life balance. By applying rules based on specific schedules, you ensure that your network resources are used efficiently. It's like having a digital traffic cop, guiding users to stay focused when it matters most. With time-based ACLs, you're not just managing access, you're optimizing performance and creating a more disciplined work environment. ACLs, or access control lists, are essential for managing network traffic in routers. Imagine a bouncer at a club. Each rule in ACL acts like a bouncer, checking IDs as packets arrive. These rules are evaluated in a strict top-to-bottom order. The first rule that matches the packet's attributes, like source, IP, or protocol, decides whether to permit or deny the traffic. Now, if none of the rules match, we hit the implicit deny. Think of it as the bouncer saying, "Sorry, you can't come in." ACLs can be applied to inbound or outbound traffic. Inbound ACLs filter packets before they enter the router, while outbound ACLs do their job before packets leave. This sequential processing ensures that only the right traffic gets through, keeping your network secure and efficient. When it comes to using ACLs in network routers, placement is key. For standard ACLs, position them close to the destination since they filter based on source IP. On the other hand, extended ACLs should be placed near the source because they evaluate multiple criteria. Now, let's talk about the order of rules. Always put the more specific rules at the top. This prevents them from being overridden by broader rules that might come later. And remember, less is more. Minimize the number of rules to only what you need for effective filtering. Before rolling out any ACLs in production, test them in a lab environment. This helps catch any issues early on. Don't forget to document your ACL configurations. It's essential for troubleshooting and auditing. Finally, make it a habit to regularly audit and update your ACLs to ensure they align with your current security policies. Keeping your network secure is all about smart management of those access control lists. Imagine a world where your network is a fortress, and access control lists, or ACLs, are the guards at the gate. First, they block traffic from known malicious IP addresses, keeping the bad guys out. Next, they restrict access to critical services like SSH and FTP, ensuring only trusted users can get in. Spoofing? Not on their watch. They prevent any traffic with invalid source IPs, like private addresses trying to sneak in from the internet. Then there's controlling internet access. ACLs can allow or deny specific websites and applications, tailoring the browsing experience for users while blocking distractions or threats. And when it comes to securing remote access, they ensure that only trusted IP addresses or VPNs can connect, safeguarding your data from prying eyes. With ACLs, you're not just managing traffic, you're building a secure, efficient network environment. Large access control lists, or ACLs, can really bog down network routers. When these lists grow, the processing overhead skyrockets, leading to noticeable performance degradation. Imagine trying to sift through a massive stack of papers just to find one document. That's what routers face with large ACLs. Then there's the complexity factor. In sprawling networks, managing ACLs can become a tangled web of rules and exceptions, making it easy to introduce errors. It's like trying to navigate a maze without a map, frustrating and risky. And let's not forget the lack of context awareness. ACLs operate on a one-size-fits-all basis, ignoring crucial details like who's accessing the network or what applications are in play. This static nature means they require constant manual updates to keep pace with ever-changing network conditions. In a dynamic environment, that's a recipe for trouble. ACLs, or access control lists, are like the gatekeepers of our networks. Imagine having the power to decide who gets in and who stays out. This is exactly what ACLs do for network traffic. They allow us to specify which data packets can pass through our routers, providing a crucial layer of security. But it's not just about blocking unwanted traffic. It's about fine-tuning our network performance. With ACLs, we can prioritize important traffic, ensuring that critical applications run smoothly while less important data takes a back seat. However, wielding this power requires careful planning. Misconfigured ACLs can lead to performance bottlenecks or even lock out legitimate users. It's a balancing act, one that demands attention and strategy. When implemented correctly, ACLs transform our networks into secure, efficient systems, safeguarding our data while optimizing performance. Network Address Translation, or NAT, is like a clever traffic cop for your data. Imagine a bustling city where multiple cars, your devices, need to get onto a busy highway, the internet. Instead of each car having its own license plate, they all share one public plate, thanks to NAT. This not only conserves valuable IP addresses, but also adds a layer of security. When your device sends a request to the internet, NAT changes its private IP address to that single public one. When the response comes back, NAT knows exactly which device to send it to. It's efficient, it's smart, and it keeps your local network safe from prying eyes. So, the next time you browse the web, remember that NAT is working behind the scenes, making sure everything runs smoothly and securely. Private and public IP addresses are essential for how we connect and communicate in the digital world. Think of private IP addresses as the exclusive club of your home network, like 192.168xx or 10.xxxx. They're used internally, allowing devices like your laptop and smartphone to talk to each other without being visible on the public internet. This keeps your data safe and your network organized. On the flip side, public IP addresses are like your home's mailing address. They're unique and routable globally, allowing devices to communicate across the vast expanse of the internet. When you browse a website or send an email, it's your public IP that makes it all possible. Understanding the difference between these two types of addresses is crucial for navigating the online world securely and efficiently. Private and public IP addresses are essential for how we connect and communicate in the digital world. Imagine a bustling city where every home has its own unique address, but only a few can be seen from the outside world. That's how private IP addresses work on local networks like 192.168xxx or 10.xxxx. They're perfect for internal communication, but invisible to the internet. Enter NAT, or Network Address Translation, the unsung hero of connectivity. When your device wants to access the web, NAT swoops in, translating those private addresses into a single public IP address. It's like a VIP pass that lets your data mingle with the global crowd. And when the internet responds, NAT is right there again, translating that public address back into the correct private one, ensuring the right device gets the message. This seamless dance translation keeps our local networks secure while allowing us to surf the web without a hitch. It's a clever solution that makes our digital lives possible, all while keeping our private addresses just that, private. Static NAT is a crucial networking technique that connects a single private IP address to a single public IP address. Imagine you have a web server or an email server that needs to be accessible from anywhere on the internet. That's where static NAT shines. It creates a direct line, ensuring that whenever someone tries to reach your server, they always hit the same public IP address. This is especially important for services that require consistent access, like hosting a website or managing email communications. With static NAT, you eliminate the guesswork. Your server is always reachable, making it reliable for users. Plus, it enhances security by keeping your internal network hidden while still allowing external access. So, if you want your services to stand out and be accessible, static NAT is the way to go. Static NAT is a crucial networking technique that connects a single private IP address to a single public IP address. Imagine you have a web server or an email server that needs to be accessible from anywhere on the internet. Dynamic NAT is like a clever traffic manager for your network. Imagine you have a private IP address, like a house number, but you need to send data out into the vast internet. Dynamic NAT steps in, mapping your private address to a pool of public IP addresses. Think of them as temporary guest passes. When your device wants to communicate, NAT quickly grabs an available public IP from that pool, allowing your data to flow seamlessly. Once the data is sent, the public IP is returned to the pool, ready for the next request. This not only conserves public IP addresses, but also adds a layer of security, keeping your internal network hidden from prying eyes. Dynamic NAT is efficient, flexible, and essential for managing the ever-growing demand for internet connectivity. It's the unsung hero of network communication, ensuring that everyone can connect without a hitch. Dynamic NAT is like a clever traffic manager for your network. Imagine you have a private IP address, like a house number, but you need to send data out into the vast internet. Imagine a bustling city where every home has its own unique address, but they all share a single main road to the outside world. That's exactly how Port Address Translation, or PAT, works in networking. It's like a clever traffic cop for your internet connection. With PAT, multiple devices on a private network can share one public IP address. How? By using different port numbers to keep their data streams separate. For instance, your laptop might send a request out as 192.168.1.1111001, while your smartphone uses 192.168.1.21002. When the responses come back, the router knows exactly where to send them, ensuring that your devices stay connected without any mix-ups. This not only conserves IP addresses, but also adds a layer of security, keeping your internal network hidden from the outside world. So, next time you browse the web, remember the magic of PAT working behind the scenes, making sure your digital life runs smoothly. NAT, or Network Address Translation, is a game changer in how we manage our IP addresses. With the limited pool of IPv4 addresses, NAT lets multiple devices in a local network share a single public IP address. Imagine your home network, your smartphone, laptop, and smart TV all connected. Yet they're all using just one public IP to communicate with the outside world. This not only conserves those precious IP addresses, but also simplifies network management. But there's more. NAT also enhances security by keeping internal IP addresses hidden from the internet. NAT, or Network Address Translation, is a game changer in how we manage our IP addresses. With the limited pool of IPv4 addresses, NAT lets multiple devices in a local network share a single public IP address. Imagine your home network, your smartphone, laptop, and smart TV all connected. Yet they're all using just one public IP to communicate with the outside world. This not only conserves those precious IP addresses, but also simplifies network management. But there's more. NAT also enhances security by keeping internal IP addresses hidden from the internet. Let's dive into the world of IP addresses and NAT. Picture this. Your device connects to the internet using an external public IP address. This is how the world sees you. But inside your home or office, things are different. You have internal private IP addresses that keep your devices communicating securely without exposing them to the outside world. Now, we talk about static NAT. The outside global IP remains the same, representing your public face, while the inside local IP is your private identity. The outside local and outside global fields, they're typically blank unless you're dealing with more complex NAT setups. This means your internal network can operate smoothly without unnecessary exposure. Understanding these concepts is crucial for anyone looking to navigate the intricacies of networking effectively. It's all about keeping your data safe while staying connected. Dynamic NAT is a fascinating process that utilizes a pool of public IP addresses to manage network traffic efficiently. Imagine a scenario where multiple internal devices need to access the internet, but they all share a limited number of public IPs. That's where the access list comes in, defining which internal IPs are allowed to use NAT. Now, let's talk about the NAT pool. This is essentially the range of public IPs that are available for translation. When a private IP wants to connect to the outside world, Dynamic NAT steps in, translating that private IP to one of the public IPs from the pool. The cool part? Each time a device connects, it might get a different public IP from the pool, making the mapping dynamic and flexible. This not only optimizes the use of IP addresses, but also enhances security, as the internal structure remains hidden. Dynamic NAT is a smart solution for managing IP addresses in a world where they are a precious resource. Dynamic NAT is a fascinating process that utilizes a pool of public IP addresses to manage network traffic efficiently. Understanding the PAT process Cisco Network Router is essential for efficient IP address management. PAT, or Port Address Translation, allows multiple devices on a local network to share a single public IP address. Imagine a busy restaurant where one chef prepares multiple dishes for different tables. Similarly, PAT maps internal IP addresses to a single external IP, using unique port numbers to keep track of each session. When a device sends a request to the internet, the router replaces the source IP with its own public IP and assigns a unique port number. When the response comes back, the router uses that port number to identify which internal device made the request, ensuring the right data gets to the right place. This not only conserves IP addresses, but also adds a layer of security by hiding internal IPs from the outside world. Understanding this process is crucial for network efficiency and security in any organization. Understanding the PAT process in a Cisco network router is essential for efficient IP address management. PAT, or Port Address Translation, allows multiple devices on a local network to share a single public IP address. IPv6, or Internet Protocol version 6, is the latest evolution of the Internet Protocol, designed to tackle the limitations of its predecessor, IPv4. With the explosion of devices connected to the Internet, IPv4's address space simply couldn't keep up. Imagine running out of addresses in a world where everything from your fridge to your car needs one. IPv6 solves this by offering an almost limitless number of unique IP addresses. About 340 undecillion to be precise. This means every device can have its own address, paving the way for innovations like the Internet of Things. Plus, IPv6 enhances security and improves routing efficiency, making our online experiences smoother and safer. As we continue to expand our digital universe, IPv6 is not just a technical upgrade, it's a crucial step toward a more connected future. IPv6, or Internet Protocol version 6, is the latest evolution of the Internet Protocol, designed to tackle the limitations of its predecessor, IPv4. Imagine a world where every device can have its own unique address, No more sharing or running out of space. That's the beauty of IPv6. With its 128-bit addresses, we're talking about a staggering 340 undecillion unique IP addresses, 3.4 times 10 to the power of 38. To put it in perspective, that's more addresses than there are stars in the observable universe. IPv4, with its 32-bit limitation, only offered about 4.3 billion addresses, which just isn't enough for our ever-growing internet. IPv6 addresses are written in hexadecimal format, divided into 8 blocks of 16 bits, separated by colons. For example, take a look at 2001 ODB8 85A3 882E 0370 7334. It might look complex, but it's a gateway to a virtually limitless digital landscape. With IPv6, we're not just expanding our address space. We're paving the way for innovation and connectivity like never before. Imagine a world where every device can have its own unique address. No more sharing or running out of space. That's the beauty of IPv6. IPv6 revolutionizes how we think about addressing in networks. First up, we have unicast addresses. These are like a direct phone line, connecting one unique sender to one unique receiver. It's straightforward, just like in IPv4. Then, there's multicast. Imagine sending a message to a group of friends instead of shouting to everyone in the room. Multicast efficiently targets multiple receivers without flooding the network. Now, let's talk about Anycast. This is where things get interesting. An Anycast address can be assigned to multiple interfaces, but the magic happens when packets are sent to the nearest one based on routing metrics. It's like having a favorite coffee shop that's closest to you, no matter where you are. And here's a key point. IPv6 eliminates broadcast addresses entirely. Instead, we use multicast, which is not only more efficient, but also reduces unnecessary network traffic. IPv6 is all about smart addressing, making our networks faster and more efficient. IPv6 revolutionizes how we think about addressing in networks. First up, we have unicast addresses. These are like a direct phone line, connecting one unique sender to one unique receiver. It's straightforward, just like in IPv4. Then there's multicast. Imagine sending a message to a group of friends instead of shouting to everyone in the room. Multicast efficiently targets multiple receivers without flooding the network. Imagine a world where your devices can talk to the network without needing a middleman. That's the magic of IPv6 stateless auto configuration. Picture this. When you connect a new device, it listens for router advertisement messages floating through the air.
These messages are like a friendly handshake, telling the device, here's how to set up your IP address. No more waiting for a DHCP server to assign an address, or dealing with manual configurations. It's seamless and efficient. This feature not only simplifies network setup, but also reduces the chances of human error.
So, whether you're at home or in a bustling office, your devices can effortlessly join the network, making life a whole lot easier. Isn't technology amazing?
Global Unicast addresses, or GUAs, are the backbone of IPv6 networking, acting like public addresses in the IPv4 world.
Imagine sending a letter across the globe. GUAs ensure that the message reaches the correct destination without confusion. In summary, GUAs play a crucial role in the functionality and efficiency of modern networking, similar to how public addresses work in traditional mail systems.
Link locals are fascinating little gems in the world of networking. These addresses are like your neighborhood's secret handshake, valid only within a local network segment or link.
They're automatically assigned to interfaces, which means you don't have to lift a finger to configure them. This makes link local addresses incredibly convenient for local communication.
In summary, linked local addresses play a crucial role in networking, allowing devices to communicate effortlessly within their local environment. They are essential for efficient.
Unique local addresses, or ULAs, are fascinating components of IPv6 networking. These addresses are designed specifically for use within a single site or organization, meaning they're not meant to be routed on the global internet. They start with the prefix FC00/7, which gives them a unique identity within your local network. Imagine you're setting up a home network or managing a corporate environment. ULAs allow devices to communicate seamlessly without the risk of external interference. For instance, an address like FCZR.1 can be assigned to a server, ensuring that it's accessible only within your local setup. This enhances security and simplifies network management. What's even cooler is that because they're not routable on the internet, you can use them without worrying about conflicts with public IP addresses. So, whether you're a tech enthusiast or a network administrator, understanding ULAs is key to building efficient and secure local networks. Multicast addresses are a game changer in networking, allowing data to be sent to multiple devices simultaneously. Imagine you're at a concert and the band plays a song that everyone loves. Instead of sending individual invitations to each fan, they just blast the music out to the crowd.
That's multicast.
Imagine a world where devices seamlessly communicate across different networks, bridging the gap between the old and the new. That's the magic of dual stack technology. By running both IPv4 and IPv6 protocols simultaneously, devices can connect effortlessly, ensuring compatibility with legacy systems while embracing the future. IPv4, with its familiar 30-bit addresses, has served us well, but it's running out of space. Enter IPv6 with its vast 128-bit address space, ready to accommodate the explosion of devices in our increasingly connected world. Dual Stack allows us to transition smoothly, letting networks communicate across both protocols without missing a beat. This means no disruptions for users, as they can access resources on either network. It's like having a universal translator for the internet, ensuring that everyone can talk to each other, regardless of which version they're using. Dual Stack is not just a technical solution. It's a bridge to a more connected future. Tunneling is a fascinating technique that allows IPv6 packets to travel seamlessly over IPv4 networks. Imagine IPv6 as a new highway, but the only roads available are old and narrow IPv4. This is where tunneling comes in. It encapsulates those IPv6 packets with IPv4 packets, creating a safe passage through the IPv4 infrastructure. Take 624, for example. It automatically assigns an IPv6 address to any device with an IPv4 address, enabling direct communication without complex configurations. Then there's Teredo, which is like a bridge for devices behind NATs, allowing them to connect to the IPv6 world even when they're tucked away behind firewalls. These tunneling methods are crucial as we transition to a more connected future, ensuring that even as we upgrade our networks, we can still communicate across different systems. It's a clever workaround that keeps the digital highways flowing smoothly, no matter the age of the infrastructure beneath. Tunneling is a fascinating technique that allows IPv6 packets to travel seamlessly over IPv4 networks. Translation between IPv4 and IPv6 networks is crucial in our increasingly connected world. Mechanisms like NAT64 play a vital role in this process. Imagine a bridge that allows two different languages to communicate seamlessly. NAT64 translates IPv4 requests into IPv6, enabling devices that only speak one version to interact effortlessly. This is essential as we transition to IPv6, which offers a vastly larger address space. Without NAT64, many devices would be left isolated, unable to connect to the growing number of IPv6-only networks. So, while IPv4 and IPv6 might seem like two different worlds, NAT64 ensures they can still share information, keeping our digital landscape interconnected and functional. In the world of IPv6, communication between devices is a fascinating dance. At the heart of this interaction lies ICMP, the Internet Control Message Protocol version 6. It's like the backbone of IPv6 networks, handling everything from address configuration to name discovery and routing. Imagine your devices sending out messages to find each other, ensuring they're on the same page. ICMPv6 is essential for diagnostics and error reporting, making it a crucial player in maintaining network health. It includes various message types like echo request and echo reply, which help us troubleshoot connectivity issues. Then there are neighbor solicitation and neighbor advertisement messages, which allow devices to discover each other on the same local network. In essence, ICMPv6 is the unsung hero of IPv6, ensuring smooth communication and operational control, all while keeping our networks running efficiently. Understanding these messages is key to navigating the complex landscape of modern networking. Router advertisements, or RAs, are like the friendly neighborhood guides of the IPv6 world. When a router sends out an RA, it's announcing its presence and sharing vital information about the network. It includes the prefix that devices use to configure their own IPv6 addresses, the default hop limit, and whether a DHCP server is available for managed configurations. Imagine a device receiving this RA, learning the prefix, and effortlessly assigning itself an IPv6 address. It's like magic. On the flip side, we have router solicitations, or RS messages. These are sent out by devices eager to join the network. When the device connects, it broadcasts an RS message, essentially asking, "Hey, any routers out there?" This prompts the routers to respond with their RAs, providing necessary details for the device to configure itself. It's a seamless dance of communication that keeps our networks running smoothly. Router advertisements, or RAs, are like the friendly neighborhood guides of the IPv6 world. When a router sends out an RA, it's announcing its presence and sharing vital information about the network. This includes the prefix that devices use to configure their own IPv6 addresses, the default hop limit, and whether a DHCP server is available for managed configurations. Imagine a device receiving this RA, learning the prefix, and effortlessly assign itself an IPv6 address. It's like magic. RAs are sent by routers to advertise their presence and provide information about the network. These messages are crucial for stateless auto-configuration and allow devices to configure their own IPv6 address. Router advertisement messages typically include prefix information for devices to configure their address, the router's default hop limit, and whether the router is a managed or other configuration. For example, a device on a network receives a router advertisement message, learns the prefix, and then assigns itself an IPv6 address within that prefix. Router solicitation messages are sent by a device to request a router advertisement message. This happens when a device joins a network and needs to discover available routers to configure itself. For example, a newly connected device broadcasts an RS message on the network to obtain the IPv6 prefix and other configuration details from a router. RAs are sent by routers to advertise their presence and provide information about the network. These messages are crucial for stateless auto-configuration and allow devices to configure their own IPv6 address. The Neighbor Discovery Protocol, or NDP, is a set of ICMPv6 messages used for the discovery of other devices on the same local network, for address resolution, and for maintaining up-to-date routing information. The neighbor solicitation message is used by a device to discover the link layer, or MAC, address of another device on the local network, similar to how ARP works in IPv4. A device sends a neighbor solicitation message to the target's IPv6 address, asking for its MAC address. The target responds with a neighbor advertisement. For example, device A needs to send a packet to device B, but it only knows device B's IPv6 address and not its MAC address. Device A sends a neighbor solicitation to discover this information. The neighbor advertisement message is sent in response to a neighbor solicitation message and contains the MAC address of the responding device. The neighbor advertisement message can also be used for the device to advertise its presence on the network or inform others about its address, including when a device's address has changed. For example, device B receives a neighbor solicitation from device A and responds with its MAC address in the neighbor advertisement message. The redirect message is used by a router to inform a device that a better next hop router is available for a specific destination. It's a method of optimizing routing and improving network performance. For example, a device is trying to reach an external network, but the router sends a redirect message to tell the device to use a different router for that destination. I want to check if a device is alive on the network. I use something called a ping. It's like sending a digital knock on the door. I send out an echo request, which is basically a message asking, "Are you there?" The device on the other end receives this request, and if it's awake and ready, it sends back an echo reply saying, "Yes, I'm here." This simple exchange is crucial for network diagnostics. It helps me troubleshoot connectivity issues, ensuring that devices are reachable. So, next time you're unsure if a device is online, remember the power of ping. It's a quick and effective way to test your network's health. These messages are used for network diagnostics to check whether a particular device is reachable and responding on the network. This message is sent by a device to check the availability of another device. It sends an echo request and waits for a response. The recipient of an echo request sends back an echo reply to confirm that the device is reachable. A device can use the ping command to send an echo request message to another device on the network and wait for the echo reply to test connectivity. These messages are used for network diagnostics to check whether a particular device is reachable and responding on the network. Imagine you're sending a message across the vast digital landscape, but suddenly it hits a wall. That's where the destination unreachable message comes into play. This is the router's way of waving a red flag saying, "Hold on, I can't get your packet to its destination." There are a few reasons for this. Maybe the destination address is just plain unreachable, like trying to call a number that doesn't exist. Or perhaps the route's blocked. Think of it as a road closure on your way to a party. Sometimes it's even due to network congestion, where too many packets are jostling for attention, and yours gets dropped in the chaos. Picture this. Your device sends out a packet, all excited to connect, but the router has to send back that dreaded message, letting you know it's not going to happen. It's a crucial part of network communication, ensuring that you're not left in the dark, wondering if your message ever made it. So, next time you see that destination unreachable, remember, it's just a network's way of keeping you informed. Imagine sending a message across the internet, but somewhere along the way, it gets stuck in a loop. That's where the time-exceeded message comes into play. Each packet of data has a time to live, or TTL, which is like a countdown timer. Every time it passes through a router, that timer ticks down. If it hits 0 before reaching its destination, the packet is discarded, and a time-exceeded message is sent back to the sender. This helps prevent endless loops in the network, ensuring that data doesn't get lost forever. So, next time you send a packet, remember, it's not just about reaching the destination, it's also about knowing when to say goodbye. Destination unreachable. This message is sent by routers or hosts to inform the sender that a destination cannot be reached for a variety of reasons, such as the destination address is unreachable, the route to the destination is unavailable, or the packet was dropped due to network congestion. For example, a device sends a packet to a destination, but there is no valid route to the destination. The router sends a destination unreachable message back to the sender. Destination unreachable. This message is sent by routers or hosts to inform the sender that a destination cannot be reached for a variety of reasons, such as the destination address is unreachable, the route to the destination is unavailable, or the packet was dropped due to network congestion. Imagine you're sending a your tracks. Imagine you're sending a large package through the internet, but suddenly a router stops you in your tracks. It sends back a packet too big message, letting you know your data is too hefty to pass through without some trimming. This message isn't just a polite suggestion, it's crucial for smooth communication. It tells you the maximum transmission unit, or MTU, that the next hop can handle. So, what do? You either slice your packet into smaller pieces or send a more compact version. This process is essential because if you ignore it, your data won't reach its destination. Think of it as a traffic cop ensuring that oversized vehicles don't clog the roads. By adhering to these size limits, you keep the data flowing efficiently, avoiding delays and ensuring that every byte gets where it needs to go. Imagine you're sending a large package through the internet, but suddenly a router stops you in your tracks. IPsec, or Internet Protocol Security, is a powerful suite of protocols that secures our online communications by authenticating and encrypting each IP packet. Imagine sending sensitive data across the internet, and with IPsec, you can rest easy knowing that your information is protected. Cisco's IPsec VPN takes this a step further, enabling secure connections between different sites or allowing remote users to access networks safely. With robust encryption methods like AES and 3DS, your data is shielded from prying eyes. Authentication is flexible too, using pre-shared keys or certificates to verify identities. Plus, integrity checks ensure that your data remains untampered throughout its journey. Whether it's site-to-site or remote access, Cisco IPsec VPN provides the security backbone that keeps our digital communications safe and sound. IPsec, or Internet Protocol Security, is a powerful suite of protocols that secures our online communications by authenticating and encrypting each IP packet. Imagine sending sensitive data across the internet. And with IPsec, you can rest easy knowing that your information is protected. Cisco's IPsec VPN takes this a step further, enabling secure connections between different sites or allowing remote users to access networks safely. Imagine being able to access your corporate network securely right from your web browser without the hassle of installing special software. That's the power of Cisco's SSL VPN. It's designed for remote access, making it perfect for those times when you need to connect to your resources, like web applications or email, on the go. With SSL VPN, you get a seamless experience. Just log in and you're in. The best part? It uses SSL TLS encryption to keep your communications secure, ensuring that your data remains private and protected. Whether you're on a laptop, desktop, or mobile device, Cisco AnyConnect solutions make it easy to stay connected and secure, no matter where you are. Imagine being able to access your corporate network securely, right from your web browser, without the hassle of installing special software. That's the power of Cisco SSL VPN. It's designed for remote access, making it perfect for those times when you need to connect to your resources, like web applications or email on the go. DMVPN, or Dynamic Multipoint VPN, is a game changer for secure communications across multiple sites. Imagine a network where you don't need a direct point-to-point connection for every remote location. That's the beauty of DMVPN. It combines IPsec for security, GRE for encapsulation, and NHRP for dynamic routing. This hybrid approach allows sites to connect on the fly, adapting to changes without the hassle of reconfiguration. It's perfect for larger networks, offering scalability and flexibility. With DMVPN, you can easily expand your network, ensuring that every remote site can communicate securely and efficiently. It's like having a virtual highway that adjusts to traffic, keeping your data flowing smoothly. Remote access VPNs are essential for anyone needing secure connectivity to their corporate network from anywhere. Imagine being able to access your work files from a coffee shop or while traveling, all without compromising security. That's where Cisco's AnyConnect Secure Mobility client shines. It supports various devices, Windows, macOS, Linux, and even mobile platforms, making it incredibly. What's more, it offers multiple VPN protocols like SSL VPN, IPsec, and IKEv2, ensuring you have options tailored to your needs. And let's not forget security. With integration for multi-factor authentication and identity management systems, your access is not just convenient, but also highly secure. So, whether you're working from home or on the go, remote access VPNs keep you connected and protected. Remote access VPNs are essential for anyone needing secure connectivity to their corporate network from anywhere. Imagine connecting multiple office locations seamlessly, as if they were all in the same room. That's the magic of a site-to-site VPN. It securely links branch offices over the internet, creating a private network without the hefty price tag of dedicated leased lines. Using robust protocols like IPsec, it ensures that your data is encrypted and authenticated, keeping prying eyes at bay. Plus, it integrates smoothly with existing routing protocols like OSPF or BGP, allowing for efficient traffic management. This means your teams can collaborate effortlessly, sharing resources and information securely, no matter where they are. A site-to-site VPN isn't just a connection. It's a powerful tool for modern organizations striving for efficiency and security in a digital world. Imagine connecting multiple office locations seamlessly, as if they were all in the same room. That's the magic of a site-to-site VPN. Cisco AnyConnect Secure Mobility is a game changer for remote work. Imagine being able to connect securely to your corporate network from virtually any device. Windows, macOS, Linux, iOS, or Android. It's all about flexibility. With its seamless connection feature, you can switch between Wi-Fi and cellular networks without ever dropping your VPN connection. This means you stay connected, even on the go. Plus, it's designed with advanced security in mind. Integration with Cisco Identity Services Engine ensures robust authentication, and multi-factor authentication adds an extra layer of protection. Whether you're in a coffee shop or working from home, Cisco AnyConnect keeps your data safe and your productivity high. Flex is a game changer in the world of virtual private networks. Imagine a solution that seamlessly combines the robustness of traditional IPsec with the cutting-edge features of IKEv2. That's FlexVPN for you. It supports a variety of VPN types, whether you need remote access for employees working from home or secure site-to-site connections between offices. The beauty of FlexVPN lies in its flexibility and scalability, making it perfect for organizations of any size. Configuration is a breeze, significantly reducing complexity for network administrators. With fast and secure negotiations powered by IKEV2, you can trust that your data is protected without sacrificing performance. Flex VPN truly redefines what VPN can do. VPN solutions are essential for securing data transmission over the internet, especially when it comes to protecting sensitive business information. Imagine setting up a remote access VPN for your team, ensuring that every connection is encrypted and private. Or consider the efficiency of a site-to-site connection linking multiple offices seamlessly. Cisco's VPN offerings are designed to meet diverse needs, whether you're looking for robust encryption, flexibility, or ease of management. When deploying a Cisco VPN, it's crucial to choose the right VPN protocol, gateway device, and client software tailored to your specific use case, be it remote, site-to-site, or mobile access. Understanding the intricacies of security protocols, authentication methods, and traffic routing is vital. This knowledge not only enhances security, but also optimizes performance, ensuring your VPN solution is both secure and efficient. With the right setup, you can confidently protect your business's most sensitive data. SNMP, or Simple Network Management Protocol, is a game changer for network administrators. Imagine being able to monitor and manage your routers and switches from anywhere, effortlessly. With SNMP, that's exactly what you get. It connects your network devices to a network management system, or NMS, which collects vital performance data and allows for remote configuration changes. At the heart of SNMP are MIBs, or Management Information Bases. These are like blueprints that define what parameters can be monitored or adjusted on your devices. Want to check bandwidth usage or track error rates? SNMP has you covered. It simplifies network management, making it easier to keep everything running smoothly. In a world where downtime is costly, having SNMP in your toolkit is essential for proactive network management. SNMP is a client-server model. The SNMP agent is the software running on a network device, such as a router, that collects data from the device, stores it, and responds to SNMP requests. The SNMP manager is the software, often referred to as a network management system, or NMS, that queries the SNMP agents, collects data, and can send configuration commands to the router or network device. The communication between the manager and agent is done using SNMP messages. These SNMP messages allow the manager to retrieve data from or send commands to the agent. SNMP is a client-server model. The SNMP agent is the software running on a network device, such as a router, that collects data from the device, stores it, and responds to SNMP requests. A management information base, or MIB, is like the brain of network management, organizing a wealth of information in a structured, hierarchical format. Think of it as a detailed map of a router's operations. Each data point or object represents critical aspects like traffic counters, interfaces, and CPU usage. These objects are identified by unique numeric strings called object identifiers, or OIDs. Each OID acts like a specific address, allowing network administrators to retrieve or set data efficiently. This structured approach not only simplifies monitoring, but also enhances troubleshooting, making it easier to maintain optimal network performance. In essence, the MIB is an essential tool that keeps our networks running smoothly and efficiently. A management information base, or MIB, is like the brain of network management, organizing a wealth of information in a structured, hierarchical format. Think of it as a detailed map of a router's operations. SNMP, or Simple Network Management Protocol, is essential for managing network devices. It operates using several key message types. First, there's the GET message, where the manager requests specific information from a router, like interface status or CPU usage. Then we have the SET command, which allows the manager to change configurations on the router, such as updating interface settings or routing protocols. Next up is the TRAP message, an alert sent from the router to the manager, notifying them of critical events, like a link going down or high CPU utilization. For more efficient data retrieval, we use GetNext, which fetches the next piece of data in a sequence, perfect for looping through tables. And when we need to pull a large amount of data at once, GetBulk comes into play, making it easier to handle extensive tables. Each of these operations plays a vital role in keeping our networks running smoothly and efficiently. SNMP, or Simple Network Management Protocol, is essential for managing network devices. It operates using several key message types. SNMP operates on several different types of messages. GET, which is a request from the manager to retrieve specific information from the router, such as interface status or CPU usage. SET is a command from the manager to change the configuration on the router, like changing interface settings or updating routing protocols. TRAP is an alert sent by the router or agent to the manager to inform about specific events, such as a link down or high CPU utilization. GetNext is a request to retrieve the next piece of data in a sequence of values, often used to loop through tables of values. Finally, GetBulk is used to retrieve a large amount of data in one request, often used for tables. SNMP operates on several different types of messages. GET, which is a request from the manager to retrieve specific information from the router, such as interface status or CPU usage. Community strings in SNMP are like the keys to a digital vault, controlling access to router data. Think of them as two distinct keys. The read-only key lets you peek inside, allowing the SNMP manager to gather information without making any changes. It's perfect for monitoring network performance without the risk of accidental alterations. On the other hand, the read-write key is more powerful, granting full access to both read and configure the router. This means you can not only see the data but also tweak settings as needed. However, with great power comes great responsibility. Misusing the RW string can lead to unintended disruptions. So, whether you're just observing or actively managing, understanding these community strings is crucial for maintaining a secure and efficient network. Community strings in SNMP are like the keys to a digital vault, controlling access to router data. SNMP, or Simple Network Management Protocol, has evolved significantly over the years. Let's dive into its versions. First up, SNMP v1. It's the original, offering basic functionality for network management, but it's like sending postcards. No encryption, no strong authentication. Then we have SNMP v2c, which steps it up with faster performance and bulk data retrieval. It's definitely an upgrade, but still lacks the security features we crave. Enter SNMP v3, the game changer. This version brings encryption and robust authentication to the table, ensuring that your data is protected during transmission. Plus, it introduces user-based access control, allowing for more granular security. In a world where data breaches are all too common, SNMP v3 is the hero we need, safeguarding our networks like never before. SNMP, or Simple Network Management Protocol, has evolved significantly over the years. Let's dive into its versions. First up, SNMP v1. It's the original, offering basic functionality for network management, but it's like sending postcards. No encryption, no strong authentication. Monitoring network interfaces is crucial for maintaining optimal performance. Using SNMP, we can easily track the status of our router's interfaces, whether they're Ethernet, serial, or wireless. Imagine being able to fetch key performance indicators like traffic load, errors, and collisions with just a simple SNMP GET request. For instance, the IFOPER status tells us if an interface is up or down, giving us immediate insights into connectivity issues. Then there are if-in octets and if-out octets, which reveal the number of octets received and transmitted. This data helps us understand traffic patterns and potential bottlenecks. And let's not forget about if-in errors and if-out errors. These metrics highlight any input or output errors, allowing us to troubleshoot before they escalate into bigger problems. By leveraging SNMP, we can ensure our network runs smoothly and efficiently, keeping everything connected and performing at its best. Monitoring router performance is crucial for maintaining a smooth network experience. By keeping an eye on CPU utilization and memory usage, we can determine if our router is under heavy load or if it needs some performance tuning. For instance, the CPU load MIB object gives us the percentage of CPU usage, allowing us to spot potential bottlenecks before they become issues. Similarly, tracking memory usage helps us understand how much memory is being utilized, which is vital for capacity planning. If these metrics are consistently high, it's a clear sign that we need to optimize our router settings or consider an upgrade. Regular monitoring not only enhances performance but also prevents frustrating downtime, ensuring our network runs efficiently. Tracking routing information
Imagine a router, quietly monitoring the network, ready to spring into action at the first sign of trouble. When an interface goes down, it doesn't just sit there. It sends an SNMP trap straight to the network management system. This alert is like a digital SOS, notifying the administrator of critical events.
Picture this. A link failure triggers a trap, or high CPU usage sends a warning signal. Even memory usage exceeding a threshold can set off alarms. Authentication failures? You bet those generate traps too. Each of these events is crucial for maintaining network health. By leveraging these traps, administrators can respond swiftly, ensuring the network runs smoothly and efficiently. It's all about keeping the digital world connected and secure. Configuration management using SNMP set commands is a game changer for network administrators. Imagine being able to change router settings from anywhere, like adjusting interface IP addresses or modifying routing protocol configurations, all with just a few commands. It's like having a remote control for your network. But here's the catch. To ensure security, these configuration changes are typically restricted to SNMP v3. This version employs strong authentication, which means only authorized users can make those critical adjustments. So, while you're fine-tuning quality of service settings or tweaking bandwidth allocations, you can rest easy knowing your network has unauthorized access. Embracing SNMP not only streamlines management but also fortifies your network's security. Its efficiency and safety rolled into one powerful tool. In the world of network management, understanding SNMP is crucial. Think of public as your read-only community string, while private gives you read-write access. This distinction is vital for maintaining security and control. When you enable SNMP traps with the command SNMP server enable traps, your router can actively communicate with your network. In the world of network management, understanding SNMP is crucial. This distinction is vital for maintaining security and control. When it comes to network management, SNMP is a powerful ally, but it's not without its pitfalls. SNMP1 and SNMP-v2c rely on community strings that are transmitted in plain text. This means anyone with the right tools can eavesdrop and potentially exploit vulnerabilities. It's like sending your passwords on a postcard, definitely not secure. Enter SNMP-v3, the game changer. With its built-in authentication and encryption, it significantly boosts security, making it the go-to choice for protecting sensitive communications. But even with SNMP-v3, we can't let our guard down. Proper access control is crucial. We need to ensure that only authorized devices and users can access the SNMP interface. So, while SNMP can be a fantastic tool for monitoring, always prioritize security to keep your network safe. When it comes to network management, SNMP is a powerful ally, but it's not without its pitfalls. SNMP-v1 and SNMP-v2c rely on community strings that are transmitted in plain text. NTP, or Network Time Protocol, is a game changer for Cisco network routers. Imagine trying to troubleshoot a network issue without right timestamps. Chaos. NTP synchronizes the router's system clock with reliable time sources, ensuring every device on the network is in perfect harmony. This precision is crucial for logging events accurately, debugging issues efficiently, and executing time-sensitive tasks like scheduling backups or enforcing security protocols. Without NTP, you risk running into discrepancies that could lead to security vulnerabilities or missed deadlines. So, when it comes to maintaining a smooth and secure network, NTP is not just a luxury, it's a necessity. Keeping time in sync is key to keeping your network running like a well-oiled machine. In the world of system logging, we categorize messages by severity to ensure swift responses. At the top, we have 0, emergency, where the system is completely unusable. This is a call to arms. Immediate action is non-negotiable. Next is 1, alert, signaling that immediate action is required to prevent escalation. Then comes 2, critical, where conditions and we act fast to avert disaster. Moving down the scale, 3, error, indicates that something has gone wrong, but it's not yet catastrophic. 4, warning, serves as a heads up, alerting us to potential issues that could escalate. 5, notice is for normal operations that still warrant attention. Think of it as a gentle nudge. 6, informational messages keep us in the loop without urgency, while 7, debug is for those deep dives into the system, helping us troubleshoot and refine. And remember, setting the timestamp for these log messages is crucial. It's not just about what happened, but when it happened. Accurate timestamps are the backbone of effective troubleshooting and system management. Syslog is an essential tool in the world of network management. Imagine a bustling city where every event, from traffic lights changing to emergency alerts, needs to be communicated efficiently. That's what Syslog does for network devices like routers and switches. It standardizes the way log messages are sent to a centralized Syslog server, allowing administrators to keep a finger on the pulse of their network. With Syslog, troubleshooting becomes a breeze. When issues arise, you can quickly sift through logs to pinpoint the problem, whether it's a faulty connection or a security breach.
Plus, it helps monitor the overall health of the network, ensuring everything runs smoothly. In a nutshell, Syslog transforms chaos into clarity, making network management not just easier, but also more effective.
If you found the content, please don't forget to like, comment, and subscribe. Your support really helps us continue to create more educational content like this. As we wrap up our complete CCNA video series, I want to express my gratitude for your engagement. Each session was designed to empower you with essential networking skills, from understanding IP addressing to mastering routing protocols. Remember, every concept we covered is a building block for your career in network engineering. Your journey doesn't end here. Keep exploring, practicing, and applying what you've learned. Together, we can elevate your expertise and tackle even more complex challenges in the future. Thank you for being part of this incredible learning experience. Like, share, subscribe to Aravind channel for more videos. In the world of networking, MAC learning is a fascinating process that keeps our data flowing smoothly. When a switch receives an Ethernet frame, it first checks the source MAC address. This is like taking attendance in a classroom. The switch records this address and links it to the specific port it came from, building a dynamic MAC address table. Now, when it needs to send data, it looks up the destination MAC address. If it finds it in its table, it knows exactly where to send the frame. Efficient and direct. But if it doesn't have that address, it broadcasts the frame to all ports, like shouting out to find a friend in a crowded room. And here's the kicker. Switch doesn't hold on to these addresses forever. After a set period, if it hasn't seen a MAC address, it removes it from the table. This aging process keeps the switch's memory fresh and helps optimize network traffic, ensuring that data reaches its destination without unnecessary delays. It's all about efficiency in the digital world.
Session layer, layer 5. Role, manages sessions or connections between applications on different devices, handling setup, maintenance, and termination of communication sessions. Functions. Coordinates communication sessions, including initiation, session control, and termination. Synchronizes data exchange and manages dialogue control between systems. Example protocols: NetBIOS, SMB, Server Message Block, PPTP, Point-to-Point Tunneling Protocol. The OSI, Open Systems Interconnection, model is a conceptual framework used to understand and standardize the functions of a networking or telecommunication system. Developed by the International Organization for Standardization, ISO, in 1984, it divides network communication into 7 distinct layers, each with specific roles and responsibilities. This layered approach helps simplify the process of networking by dividing it into manageable parts, enabling interoperability among various hardware, software, and protocols. Point-to-point topology. A simple layout where two devices are directly connected by a single cable or wireless link, creating a dedicated connection between them. Advantages. Simple to set up and provides a direct, high-speed link between two devices. No data collisions, as there's only one direct connection. Disadvantages. Limited to only two devices. Not scalable for larger networks. Use cases: often used for direct connections between two important devices or between two network locations in a larger network. Physical layer, Layer 1. Role, responsible for the actual transmission of raw data bits, zeros and ones, over a physical medium like cables, radio frequencies, or fiber optics. Functions. Defines hardware components, including cables, switches, and network interface cards, NICs. Manages electrical signals, voltage levels, data rates, and other physical specifications. Example devices/technologies, Ethernet cables, fiber optics, hubs, Wi-Fi radios. Point-to-multipoint topology. Description: a central device is connected to multiple other devices, which do not connect to each other directly. It's often used in wireless networks where one access point connects to multiple devices. Advantages: simple and cost-effective for connecting multiple devices. Easy to expand by adding more endpoints. Disadvantages: bandwidth can be limited as multiple devices share the central connection. Central device failure can impact all connected devices. Use cases, common in wireless and WAN networks, particularly in environments like Wi-Fi hotspots. Each topology has its strengths and weaknesses, and the choice depends on factors like network size, cost, scalability needs, fault tolerance, and maintenance complexity.
SSH operates on a client-server model, and it's fascinating how it establishes a secure connection. Picture this. The client reaches out to the SSH server, and the server responds by sending its public key. This is where the authentication begins. The client checks the server's authenticity against stored host keys, ensuring it's connecting to the right place. Now let's talk about authentication methods. The client chooses from several options. There's password authentication, which is less secure, but then there's public key authentication, a much stronger choice. For enterprise environments, Kerberos authenticates in, adding another layer of security. Once authenticated, SSH creates a secure encrypted tunnel. This means all data, commands, files, everything travels through this tunnel, shielded from prying eyes. It's a robust system that keeps our communications secure and private. Isn't it amazing how SSH combines security and convenience? SSH has a variety of cryptographic algorithms to ensure secure communication. First, we have key exchange algorithms, crucial for establishing a shared secret key. Diffie-Hellman is a classic choice, but beware of the weak group 1-SHA-1. Opt for the secure group 14-SHA-256, or the more efficient ECDH. For top-notch security, Curve 25519 is highly recommended. Next, let's talk about authentication algorithms to verify client authenticity. RSA is still popular, but make 2048-bit or higher. DSA is outdated and weak, while ECDSA is preferred for efficiency. The strongest option, ED25519. Comes to encrypting, symmetric encryption algorithms like AES are the go-to, with options for 128, 192, or 256-bit encryption. ChaCha20 Poly 1305 is another fast and secure choice. while 3DES is a no-go due to its weaknesses. For AES, AES CTR is recommended for security, and AES GCM offers both security and efficiency. Finally, message authentication codes, which ensure data integrity. HMAC SHA-226 is the standard recommendation, with HMAC SHA-25 being even stronger. Just clear of HMAC MD5, it's weak and not suitable for secure applications. Each of these algorithms plays a vital role in keeping our SSH connections safe and sound. SSH, or Secure Shell, is a powerful cryptographic network protocol that ensures secure remote access, command execution, and file transfers over unencrypted networks. Unlike outdated protocols like Telnet, which expose data and text, SSH encrypts everything, protecting it from eavesdroppers. It boasts key features like robust encryption, secure authentication, and data integrity, making it a go-to for secure communications. SSH has two versions, SSH-1, which is deprecated due to vulnerabilities, and SSH-2, the current standard that employs advanced cryptographic algorithms. Connect to an SSH server starts with a secure handshake where the server shares its public key. You authenticate using methods like password or public key authentication, establishing a secure tunnel for all your data. SSH utilizes various cryptographic techniques, including key exchange algorithms like Diffie-Hellman and ECDH, ensuring a shared secret key is safely established. For authentication, RSA and ED 25519 are preferred, while AES and CHA-20 Poly 1305 are encrypting data. With SSH, you can confidently execute commands and transfer files, knowing your information is secure and intact.
Hybrid topology. A combination of two or more of the basic topologies, example star bus, star ring. Designed to meet specific network requirements. Advantages. Flexible and can adapt to different requirements. Scalable and customizable. Disadvantages. Can be expensive and complex to implement. Troubleshooting and maintenance can be challenging due to mixed layouts. Use cases, common in large networks with complex needs, like campus environments or multi-floor office buildings. What is mesh topology in networking? In a mesh topology, each device is connected to multiple other devices, creating multiple paths for data to travel. It can be full mesh, every device connects to every other device, or partial mesh, some devices connect to multiple others, but not all. Advantages. Very fault tolerant, as data can reroute if one path fails. High redundancy and reliability. Disadvantages. Requires a large number of cables and can be costly. Complex to set up and manage, especially for large networks. Use cases, common in large, critical networks that require high reliability, such as data centers and WANs. What is ring topology in networking? Each device is connected to exactly two other devices, forming a closed loop or ring. Data travels in one direction around the ring until it reaches its destination. Advantages: easy to install and manage for small networks. Data can travel quickly, as it follows a designated path. Disadvantages: a break in the ring can bring down the network unless dual ring or redundant ring technology is used. Not easily scalable, and troubleshooting can be challenging. Use cases: used in some specific network types like token ring, but less common in modern Ethernet networks. What is star topology in networking? All devices are connected to a central hub or switch. Each device has its own cable connecting it to this central device, which directs traffic. Advantages: easy to install and manage. A failure in one cable only affects one device, making it fault tolerant. High performance, as each device has a dedicated connection. Disadvantages: relies on the central hub or switch. If it fails, the entire network goes down. Requires more cabling than a bus topology. Use cases: common in home networks and small to medium business networks. Network layer, Layer 3. Role: responsible for logical addressing, example IP addresses, and routing, determining the best path for data to reach its destination across networks. Functions: handles packet forwarding, routing, and addressing. Manages traffic control to prevent network congestion. Example protocols: IP, Internet Protocol, ICMP, Internet Control Message Protocol, OSPF, Open Shortest Path First, BGP, Border Gateway Protocol, iGroup or IPv1/2. Example devices: routers.
The TCP/IP model is the backbone of Internet communication, structured into 4 essential layers. At the top, we have the application layer, where user-facing protocols like HTTP and FTP facilitate everything from web browsing to email. Below that, the transport layer ensures reliable data delivery, with TCP providing a secure connection, while UDP offers speed without guarantees. Next is the Internet layer, responsible for routing packets across networks using IP, whether it's IPv4 or the newer IPv6. Finally, the network access layer handles the nitty-gritty of data transmission over physical mediums like Ethernet and Wi-Fi. Unlike the OSI model, which has 7 layers, TCP/IP is streamlined and practical, making it the go-to framework for real-world networking. Understanding these layers is crucial for grasping how data travels seamlessly across the globe.
Transport layer, Layer 4. Role: ensures reliable data transfer between devices, handling error correction, data flow, and retransmission if necessary. Functions: TCP, Transmission Control Protocol, provides reliable, connection-oriented communication with error checking and acknowledgements. UDP, User Datagram Protocol offers connectionless, faster communication without guaranteed delivery. Example protocols, TCP, UDP. Example devices, firewalls, they filter traffic based on port numbers at this layer. Tree, or hierarchical, topology. A hybrid topology that combines star and bus topologies. Devices are connected in groups, stars. With each group connected to a central backbone, bus. Advantages. Allows easy expansion of the network. Fault in one group does not affect the entire network. Disadvantages. Heavily depends on the backbone. If it fails, the whole network can go down. Requires careful planning and can be complex to manage. Use cases, used in large corporate networks that need scalability and structured organization.
A collision domain is like a busy intersection where data packets can crash into each other. Imagine two cars trying to cross at the same time. Chaos ensues. In networking, this happens when multiple devices send data simultaneously, causing packet loss and frustrating delays as they scramble to retransmit. To keep the traffic flowing smoothly, we can use switches instead of hubs. Switches create separate collision domains for each device, reducing the chance of a crash. Implementing full duplex communication is another game changer, allowing devices to send and receive data at the same time. No more waiting in line. And let's not forget about segmenting networks with VLANs or routers, which further minimizes collisions. By taking these steps, we can ensure our data travels efficiently and reliably, avoiding the gridlock of a collision domain. MAC addresses are fascinating, but they come with limitations. First off, they only work within a local network, like your home Wi-Fi. Once data hits a router, it's all about IP addresses. Think of MAC addresses as your street address. Great for local delivery. But once you're outside the neighborhood, it's the postal code that matters. And here's the kicker. Routers don't even look at MAC addresses when sending data across networks. They rely solely on IP addresses to figure out where to send your information. But there's more. MAC addresses can be a privacy concern. They can track your device as it hops from one network to another, raising red flags about your personal data. To combat this, many devices now use randomized MAC addresses when connecting to Wi-Fi, adding a layer of privacy. So, while MAC addresses are essential for local communication, they definitely have their drawbacks. The enable password in a Cisco network device is crucial for securing access to privileged exec mode. This mode is where the magic happens, executing administrative commands, configuring interfaces, managing routing, and tweaking security settings. Now, let's talk about the difference between the to encrypt the password, making it much more secure. So, what's the best practice? Always opt for the enable secret. It's a simple switch that can save you from potential security breaches. Protect your network like a pro. In the world of networking, speed is everything. It's all about how fast data zips through your network, measured in Mbps or GBps. Think of it like a highway. The wider the lanes, the more cars can zoom by. We start with 10 Mbps Ethernet, the original standard, then leap to 100 Mbps fast Ethernet, which is 10 times faster. Gigabit Ethernet takes us to 1 Gbps, a game changer for data-heavy tasks. And then there's 10 Gbps, perfect for data centers, and even higher speeds like 25, 40, and 100 Gbps for enterprise environments. But speed isn't just about numbers. It's about performance. Higher speeds mean quicker file transfers and smoother streaming. Compatibility is key too. If your devices don't match speeds, you could hit a bottleneck. That's where auto negotiation comes in, allowing devices to automatically find the best speed for optimal performance. So, whether you're streaming your favorite show or transferring large files, UDP operates at the transport layer of the OSI model, and it's all about speed and simplicity. Unlike TCP, UDP is a connectionless protocol, meaning it doesn't waste time setting up a connection before sending data. It just fires off packets, which is great for applications where speed is crucial, like online gaming or video streaming. However, this comes with trade-offs. UDP has limited error correction. It uses a checksum to check for errors, but that's about it. It's a best effort protocol, which means it doesn't guarantee delivery. If a packet gets lost, it won't be resent. There are no data recovery features. So if you need reliability, UDP might not be your best choice. But for real-time applications where every millisecond counts, UDP shines by keeping things fast and efficient. UDP operates at the transport layer of the OSI model, and it's all about speed and simplicity. Unlike TCP, UDP is a connectionless protocol, meaning it doesn't waste time setting up a connection before sending data.
A computer is an electronic device designed for data processing, storage, and retrieval. It executes software instructions to perform tasks ranging from simple calculations to complex simulations. Due to their speed and accuracy, computers are essential in almost every industry. They handle vast amounts of information efficiently, revolutionizing how tasks are completed. From business operations to scientific research, computers enhance productivity and innovation. Their versatility makes them indispensable tools for problem-solving and data analysis. As technology advances, computers continue to evolve, offering greater capabilities and connectivity.
A domain name is like the friendly face of the internet. Instead of memorizing a string of numbers, like an IP address, let's say 142.250.190.14, you can just type in google.com. It's much easier, right? Think of it as an alias that helps navigate the vast digital landscape.
Every website and network device has its own unique IP address, but domain names make it accessible for everyone. They bridge the gap between complex numerical addresses and our human need for simplicity. So, the next time you hop online, remember that behind every domain name is a series of numbers. But thanks to these names, we can surf the web without a second thought.
It's all about making our online experience smoother and more intuitive. A domain name is like the friendly face of the internet. Instead of memorizing a string of numbers, like an IP address, let's say 142.250.190.14, you can just type in google.com. It's much easier, right? A network device banner is more than just a message. It's your first line of communication with users accessing a Cisco device. Imagine logging in and being greeted by a message of the day or MOTD banner. This is where you can display crucial legal disclaimers or system notifications like unauthorized access is prohibited. It sets the tone right from the start. Then there's the login banner, which pops up just before users enter their credentials. This is your chance to reinforce security, reminding users of the importance of safeguarding their access. Finally, after a successful login, the exec banner takes the stage. Here, you can share system details, like the last login time, keeping users informed about their session. Each banner serves a purpose, ensuring that users are aware and alert before diving into the system. It's all about creating a secure and informed environment. Each banner serves a purpose, ensuring that users are aware and alert before diving into the system. It's all about creating a secure and informed environment. IPv4, or Internet Protocol version 4, is the backbone of Internet communication, operating at the network layer of the TCP/IP model. With its 32-bit address system, it supports around 4.3 billion unique IP addresses, formatted in the familiar dotted decimal notation. IPv4 categorizes addresses into 5 classes, from Class A for large networks to Class E for experimental use. One of its key features is subnetting, which allows networks to be divided into smaller, manageable subnetworks using subnet masks. However, IPv4 is a connectionless protocol, meaning it sends data without establishing a dedicated connection, relying on best effort delivery. This means no guarantees on packet delivery or order. Those are handled by higher layer protocols like TCP. The IPv4 header is packed with essential metadata, including source and destination addresses, and even a checksum for integrity. Despite its simplicity and widespread adoption, IPv4 faces limitations like address exhaustion and a lack of built-in security. This has led to the development of IPv6, which offers a much larger address space and improved features. Yet IPv4 remains a crucial part of our digital landscape, operating alongside IPv6 in many networks today. An ARP reply is a crucial part of how devices communicate on a local network. Imagine computer A sending out an ARP request asking, "Who has IP address XXXX?" This is like sending a shout into the network, hoping for a response. When computer B, the device that owns that IP address, hears the request, it responds with an ARP reply. This reply is a direct message back to computer A, containing its MAC address, the hardware address that allows for communication. What's fascinating is that this reply is unicast, meaning it goes straight to the requester, not broadcast to everyone. Once computer A receives this ARP reply, it stores the IP to MAC mapping in its ARP cache. This cache is essential because it allows computer A to send future packets directly to computer B without needing to ask again. In essence, the ARP reply is the missing link that connects IP addresses to MAC addresses, enabling seamless communication at layer 2 of the OSI model. It's a simple yet powerful mechanism that keeps our local networks running smoothly. An ARP request is like sending a friendly shout-out in a crowded room. Imagine you need to connect with a friend, but you only know their name, no clue where they are. So, you broadcast, "Who has the IP address XXXX? Please share your MAC address." This is how devices communicate on a local network. When the device with that IP hears your call, it responds with its MAC address, like saying, "Here I am." Now you can chat directly. But it doesn't stop there. To save time for future conversations, your device remembers this IP to MAC mapping in its ARP cache. This process is crucial for smooth communication within local networks, ensuring that data packets reach their intended destinations efficiently. ARP is the unsung hero of networking, making sure devices can find each other and connect seamlessly. ARP is the unsung hero of networking, making sure devices can find each other and connect seamlessly. An ARP table is like a phone book for devices on a local network. It maps IP addresses to MAC addresses, allowing devices to communicate seamlessly. Think of the IP address as a logical address, guiding data across networks, while MAC address is the physical identifier, like a home address for your device. When one device wants to talk to another, it first checks its ARP table. If it doesn't find the MAC address, it sends out an ARP request asking who has this IP address. The device with the matching IP responds with its MAC address, and voila! This mapping is stored in the ARP table for future use, making communication faster and more efficient. Entries can be dynamic, learned through these requests, or static, manually set. So, the next time you connect to a network, remember the ARP table is working behind the scenes, ensuring your data gets to the right destination.
Bus topology. All devices are connected to a single central cable, known as the bus or backbone. Data sent from a device travels along the bus and is received by all other devices on the network. Advantages: easy to set up and extend. Requires less cabling than other topologies. Low cost for small networks. Disadvantages: limited scalability and poor performance with large numbers of devices. A break in the bus cable can take down the entire network. High chances of data collisions, leading to slower speeds. Use cases: small networks or temporary network setups where cost is a priority.
Command line interface, or CLI, is like a secret weapon for network administrators. It's a text-based interface that lets us interact directly with networking devices. Think routers, switches, and firewalls, using just our keyboard. Unlike graphical interfaces where you click buttons and navigate menus, CLI demands precision. You type commands like ping to check connectivity or traceroute to track data paths. The beauty of CLI lies in its efficiency. For experienced users, it's lightning fast, perfect for troubleshooting or automating tasks. Plus, it gives us full access to a device's capabilities, including advanced configurations that might be hidden in a GUI. Take Cisco's iOS for instance. Commands like show IP interface brief provide instant insights into network interfaces. And with tools like SSH, we can manage devices remotely, making our lives a lot easier. In a world where speed and control matter, mastering the CLI is essential for anyone serious about networking. A console cable is a crucial tool for anyone managing network devices. It connects directly to the console port of a router or switch, allowing you to access the command line interface, or CLI. This is especially handy when the device isn't yet configured or reachable over the network. There are different types of console cables. The RS-232 serial console cable is common for older devices, while modern ones often use an RJ45 connector. If your laptop lacks a serial port, a USB to serial adapter comes to the rescue. Some newer devices even feature a direct USB console port, making connection simpler than ever. Using a console cable is straightforward. You connect it between your computer and the device, then fire up terminal emulator software like PuTTY. This gives you power to configure, troubleshoot, and manage your network devices directly. Whether it's for initial setup or recovery, a console cable is indispensable for effective network management. A console cable is a crucial tool for anyone managing network devices. It connects directly to the console port of a router or switch, allowing you to access the command line interface, or CLI. This is especially handy when the device isn't yet configured or reachable over the network. A console cable is a crucial tool for anyone managing network devices. It connects directly to the console port of a router or switch, allowing you to access the command line interface or CLI. This is especially handy when the device isn't yet configured or reachable over the network. There are different types of console cables. The RS-232 serial console cable is common for older devices, while modern ones often use an RJ45 connector. If your laptop lacks a serial port, a USB to serial adapter comes to the rescue. Some newer devices even feature a direct USB console port, making connection simpler than ever. Using a console cable is straightforward. You connect it between your computer and the device, then fire up terminal emulator software like PuTTY. This gives you power to configure, troubleshoot, and manage your network devices directly. Whether it's for initial setup or recovery, a console cable is indispensable for effective network management. A console cable is a crucial tool for anyone managing network devices. It connects directly to the console port of a router or switch, allowing you to access the command line interface or CLI. This is especially handy when the device isn't yet configured or reachable over the network. CSMACD, or Carrier Sense, multiple access with collision detection, is a fascinating protocol that keeps our networks running smoothly. Imagine a busy intersection where cars can only go when the road is clear. That's what Carrier Sense does. Devices listen to the network before they transmit. If it's clear, they send their data. But here's the catch. With multiple devices sharing the same medium, collisions can happen when two devices transmit at the same time. That's where collision detection comes in. When a collision occurs, both devices stop, send out a jam signal to alert others, and then wait a random amount of time before trying again. This clever back-off strategy reduces the chances of another collision. However, as networks evolve to full duplex communication and switched environments, the need for CSMACD has faded. Today, it's a relic of early Ethernet networks, ensuring that back in the day, devices could share the network without chaos. DHCP, or Dynamic Host Configuration Protocol, is a game changer in network management. Imagine a device, like your laptop or smartphone, wanting to connect to a network. It starts the DORA process with a DHCP discover message, broadcasting its need for an IP address. Then, the DHCP server jumps in with a DHCP offer, presenting an available IP address along with essential network details like the subnet mask and DNS servers. Once the device receives this offer, it sends back a DHCP request, confirming it wants that IP address. Finally, the server responds with a DHCP acknowledgement, officially assigning the IP address for a specific lease time. This whole process simplifies our lives by eliminating the need for manual IP address assignments, ensuring efficient use of IP addresses and preventing conflicts. DHCP makes networking smooth and hassle-free, allowing devices to connect seamlessly. When it comes to data transmission, TCP and UDP are like two sides of a coin. TCP, or Transmission Control Protocol, is your reliable friend. It ensures that every piece of data arrives in the correct order, thanks to its error checking and connection setup. Sure, it comes with some overhead, but for tasks like browsing the web or sending emails, that reliability is crucial. On the flip side, we have UDP, or User Datagram Protocol. Think of it as the speedster of the data world. It's fast and efficient, perfect for real-time applications like streaming or online gaming. But here's the catch. It doesn't guarantee that your data will arrive in order or even at all. So, if you're watching a live game, a little data loss might not matter as much as the thrill of the moment. In summary, choose TCP when you need reliability and order, and go for UDP when speed is your top priority. Each has its place in the digital landscape, catering to different needs. Duplex is all about how data flows between devices. Think of half duplex like a walkie-talkie. You can talk or listen, but not at the same time. This can lead to collisions, especially in shared networks like Ethernet, where devices might step on each other's toes. Now, full duplex is a game changer. It's like a phone call. Both parties can chat and listen simultaneously, doubling the efficiency of communication. When it comes to network interface cards or switches, choosing the right duplex mode is crucial. If one device is set to full duplex and another to half duplex, you could face performance issues like packet loss and reduced throughput. Modern devices often support auto negotiation to find the best settings, but sometimes manual tweaks are necessary. Getting this right ensures smooth, efficient data transmission, keeping your network running at its best. Enable mode, or privileged exec mode, is where magic happens on Cisco devices. Once I type the enable command from user mode, the prompt shifts to router IO, signaling that I've unlocked a treasure trove of commands. Here, I can dive into configuration commands like configure terminal, run diagnostics with ping and traceroute, and access system commands like reload and show running config. This mode operates at privilege level 15 by default, giving me the keys to the kingdom. But it's not all open doors. I might need to enter an enable password or a more secure enable secret to gain access. From here, I can transition to global configuration mode with just a simple conf-t, where the real configuration changes take place. In enable mode, I'm empowered to manage and configure the device, ensuring everything runs smoothly. It's all about control and capability, making it an essential part of network management. In networking, a hostname is like a friendly nickname for a device on the network. Instead of remembering a string of numbers, like an IP address, you can just think of laptop 01 or printer 01. It's much easier. On the internet, these hostnames are part of domain names, like www.google.com, and the domain name system, or DNS, does the heavy lifting by translating those names into IP addresses so devices can communicate seamlessly. On local networks, host names help us identify devices quickly. You can configure them manually or let services like DHCP assign them automatically. Each host name is unique to a device, and there are some rules to follow. They can include letters, numbers, and hyphens, but they can't start or end with a hyphen. And remember, a fully qualified domain name can be up to 255 characters long. So when you type ping laptop 01, your system resolves that host name to its IP address, like 192.168.0.15, and sends the ping request. It's a simple yet powerful way to keep our networks organized and user-friendly. IPv4 has served us well, but its limitations are becoming increasingly apparent. Enter IPv6, the game changer, with its massive 128-bit address space. Imagine the possibilities. No more running out of IP addresses, which is crucial as we connect more devices. Think mobile phones, smart appliances, and the Internet of Things. IPv6 also brings built-in security features, making our online interactions safer. Plus, it's designed for efficiency, optimizing data flow and reducing latency. While IPv4 is still hanging around, most networks are now operating in dual stack mode, allowing them to support both protocols seamlessly. This transition is not just a technical upgrade. It's a leap into a more connected and secure future. IPv4 has served us well, but its limitations are becoming increasingly apparent. Enter IPv6, the game changer with its massive 128-bit address space. A MAC address, or Media Access Control Address, is like a fingerprint for your network devices. Each one is unique, hard-coded by the manufacturer. ensuring that no two devices on the same local network share the same identifier. This uniqueness is crucial for communication at the data link layer of the OSI model, where protocols like Ethernet operate. Typically, a MAC address is a 48-bit hexadecimal number, often displayed in formats like 01 to 23 part 45 67 89 AB. The first half, known as the organizationally unique identifier, is assigned to the manufacturer by the IEEE, while the second half is used to identify the specific device. Unlike IP addresses that can change, a MAC address remains static for the device's lifetime, making it a reliable way to identify devices on a network. However, some devices can spoof or change their MAC addresses, adding an interesting twist to network security. Understanding MAC addresses is essential for managing and securing networks effectively. A MAC address, or Media Access Control Address, is like a fingerprint for your network devices.
Computer networking involves connecting computing devices to enable communication and resource sharing, enhancing efficiency and coordination among devices. Key devices in a network include computers, smartphones, servers, routers, and switches, all participating in data exchange. Protocols like TCP/IP set rules for transmitting and receiving data across networks, ensuring seamless communication. Data travels across networks via physical media like cables or wirelessly, such as through Wi-Fi, enabling connectivity. Networks vary in size and purpose, from local area networks, LANs, to wide area networks, WANs. Networking forms the backbone of the Internet, supporting global information and resource sharing across interconnected networks. It powers essential functions like web browsing, email, video conferencing, and file sharing, integral to modern computing.
In networking, a physical topology refers to the physical layout or arrangement of devices and cables in a network. The type of physical topology impacts how devices communicate, how data flows, and how scalable and fault-tolerant the network is. Here are the main types of physical topologies used in networking.
The Ping tool is your go-to network diagnostic buddy, helping you check if your computer can reach another device on the network. To use it, just open your command prompt or terminal and type ping followed by the host name or IP address. For example, ping 8.8.8.8 to reach Google's DNS server. When you hit enter, you'll see replies that tell you the destination is reachable. Look for reply from, that's a good sign. The time XMs shows how long it took for the packet to make the round trip, and TTL indicates how many hops it took. Want to keep pinging? Just use ping T on Windows to run it indefinitely. Or, if you want to limit the number of pings, use ping and count for Windows, or ping C count for Linux and Mac OS. You can even specify the packet sizes with L or S. This tool is perfect for checking if a website is up, testing local connections, or troubleshooting network issues. So next time you're unsure about connectivity, just ping it. Private IP addresses are like the secret identities of devices within a network. They allow devices to communicate directly with each other without exposing themselves to the outside world. Imagine your laptop chatting with your printer or smart TV, all using these private IPs to keep their conversations safe and secure. Now, when one of these devices wants to access the internet, things get interesting. The router steps in with a clever trick called NAT, or Network Address Translation. It replaces the device's private IP with its own public IP, acting like a gatekeeper. So, when your laptop sends a request online, it's the router's public IP that gets seen by the outside world. When the response comes back, NAT translates it again, directing the data back to the correct private IP. This seamless process keeps our devices connected while protecting our internal network from outside threats. It's a brilliant dance of technology that keeps our digital lives running smoothly. Let's dive into some fascinating reserved IP ranges that go beyond the usual private ones. First up, we have the loopback addresses, ranging from 127.0.0 to 127.255.255.255. This is your computer's way of talking to itself, with 127.0.0.1 being the superstar of the show, often called localhost. It's like a virtual mirror for testing network applications without leaving your machine. Next, we encounter link local addresses from 169.254.0.0 to 169.255.255.255. These are like the safety net for devices that can't find a DHCP server. When your device can't get an IP address from a router, it assigns itself one from this range, allowing for local communication on the same network. Lastly, we have the mysterious range reserved for future use, from 240.0.0 to 255.255.2555.254. What's in store for these addresses? That's still a mystery, but it's exciting to think about the possibilities. These reserved ranges play crucial roles in networking, ensuring smooth communication and testing in our digital world. Let's dive into some fascinating reserved IP ranges that go beyond the usual private ones. First up, we have the loopback addresses, ranging from 127.0.0.0 to 127.255.255.255. This is your computer's way of talking to itself, with 127.1 being the superstar of the show, often called localhost. It's like a virtual mirror for testing network applications without leaving your machine. Private IP addresses are fascinating little gems of the networking world. They're reserved for use within private networks, which means they can't be accessed directly from the public internet. This is where network address translation, or NAT, comes into play, allowing devices with private IPs to surf the web safely. Now let's talk ranges. The Internet Assigned Numbers Authority, or IANA, defines these ranges in RFC 1918 for IPv4. We have Class A spanning from 10.0.0.0 to 10.255.255.255, which offers a whopping 16.7 million addresses. Then there's Class B from 172.6.0.0 to 172.31.255.255, providing around a million addresses. Finally, we have Class C, covering 192.168.00 to 192.168.255.255, with about 65,536 addresses. These private IP ranges are essential for managing networks efficiently, keeping our devices connected without cluttering the public internet. It's a clever system that keeps our digital lives running smoothly. Private IP addresses are fascinating little gems of the networking world. They're reserved for use within private networks, which means they can't be accessed directly from the public internet. This is where network address translation, or NAT, comes into play, allowing devices with private IPs to surf the web safely. Now let's talk ranges. The Internet Assigned Numbers Authority, or IANA, defines these ranges in RFC 1918 for IPv4. We have Class A spanning from 10.0.0.0 to 10.255.255.255, which offers a whopping 16.7 million addresses. Then there's Class B from 172.6.0.0 to 172.31.255.255, providing around a million addresses. Finally, we have Class C, covering 192.168.00 to 192.168.255.255, with about 65,536 addresses. These private IP ranges are essential for managing networks efficiently, keeping our devices connected without cluttering the public internet. It's a clever system that keeps our digital lives running smoothly. Subnetting is a powerful tool that allows us to divide a single network into smaller, more manageable subnetworks. Imagine a bustling city where each neighborhood has its own unique identity. That's what subnetting does for IP addresses. By using a subnet mask like 255.255.255.0, we can clearly define which part of the address identifies the network and which part identifies the individual devices or hosts within that network. This division not only enhances security by isolating traffic, but also improves performance by reducing congestion. Think of it as creating exclusive lanes on a highway, allowing data to flow smoothly without unnecessary delays. Plus, it makes network management a breeze. So whether you're connecting a few devices or scaling up to thousands, subnetting is the key to efficient networking. It's like having a well-organized toolbox, everything in its right place, ready for action. Subnetting is a powerful tool that allows us to divide a single network into smaller, more manageable subnetworks. Imagine a bustling city where each neighborhood has its own unique identity. That's what subnetting does for IP addresses. TCP, or Transmission Control Protocol, is a fundamental player in the Internet Protocol suite. Imagine sending a message. Before it even leaves your device, TCP establishes a connection with the receiver through a three-way handshake. This ensures both parties are ready to communicate. What's fascinating is its reliability. TCP guarantees that data arrives intact and in the right order. If any packets get lost or corrupted, it automatically requests a resend. It's like having a safety net for your data. Then there's flow control. TCP cleverly manages how much data is sent, preventing the receiver from feeling overwhelmed. It uses windowing to adjust the flow based on available buffer space. Error checking is another key feature. Each packet includes a checksum to verify its integrity. If something's off, the receiver can ask for a replacement. And let's not forget acknowledgements. Once data is received, the receiver sends an ACK back to the sender. If the sender doesn't get that acknowledgement, it knows to resend the data. Finally, TCP ensures that everything arrives in the order it was sent, even if packets take different routes. It's like a well-orchestrated symphony, delivering data seamlessly to the application layer. TCP truly makes our digital communication reliable and efficient. The Show IP Interface Brief command is a powerful tool in Cisco routers that gives you a quick snapshot of all interfaces. When you run this command, you'll see a table displaying the interface names, their assigned IP addresses, and whether they're operational. For example, if you look at Fast Ethernet 00, you might find it has the IP address 192.168.1.1, and both its status and protocol are up. This means it's ready to go. On the other hand, if you see an interface listed as administratively down, like Fast Ethernet 01, it's been manually shut down. The OK column tells you if the IP configuration is valid, while the method column reveals how the IP was assigned, either manually or via DHCP. This command is essential for troubleshooting. It allows you to quickly assess which interfaces are active and properly configured, helping you resolve issues efficiently. So, next time you're in a bind, remember to check this command for a clear overview of your router's interface status. Imagine two devices wanting to chat, like a client and a server. They can't just jump into a conversation. They need to establish a connection first. This is where the three-way handshake comes into play. It all starts with the SYN, where the sender sends a request to kick things off. Think of it as saying, "Hey, I want to connect." Then the receiver responds with a SYN-ACK, acknowledging that request. It's like saying, "Got your message, I'm ready to chat." Finally, the sender wraps it up with an AK, confirming that the acknowledgement was received. And just like that, the connection is established. This handshake ensures both devices are on the same page before they start exchanging data, making communication smooth and reliable. It's a simple yet powerful process that keeps our digital conversations flowing seamlessly. User mode in Cisco network devices is where it all begins. When you first log in, you find yourself in this default mode, represented by a prompt that looks like router or switch. Here, your access is limited. Think of it as the observation deck of a high-tech building. You can peek at the device's status and configuration with basic commands like show version or show interfaces, but don't expect to make any changes. This is read-only territory, where you can monitor and troubleshoot, but not alter the setup. User mode operates at the lowest privilege level, level 1. If you want to dive deeper and make configuration changes, you'll need to switch to privileged exec mode by typing enable. Just remember, if a password is set, you'll need that too. So, while user mode is great for getting a glimpse of what's happening, to really take control, you'll need to elevate your access. Wireshark is an incredible tool for anyone diving into the world of network analysis. Imagine being able to capture every packet zipping through your network, whether it's on your local machine or a remote server. With its powerful filtering capabilities, you can zero in on specific protocols, IP addresses, or ports, making troubleshooting a breeze. It supports hundreds of protocols from TCP to HTTP and decodes them into a detailed, human-readable format. You can analyze traffic in real time or sift through saved PCAP files, giving you flexibility in your investigations. The layered view of data helps you understand everything from the physical layer to the application layer, making complex information digestible. And if you're concerned about security, Wireshark can even decrypt SSL TLS traffic, provided you have the keys. Just remember, while it's a powerful ally for network troubleshooting and cybersecurity analysis, it's crucial to handle sensitive data ethically. With Wireshark, you're not just observing your network, you're mastering it. Wireshark is an incredible tool for anyone diving into the world of network analysis. Imagine being able to capture every packet zipping through your network, whether it's on your local machine or a remote server. With its powerful filtering capabilities, you can zero in on specific protocols, IP addresses, or ports, making troubleshooting a breeze. Imagine navigating.
I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up.
I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement. I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement. Everything I do so instinctive and so passionate. Every word I move so descriptive like an adjective. I got a vendetta against people who patented being negative when you should be getting after it. I got facts over tracks, this and that. Spitting slow, spitting fast. I could roast, I could gas. Think I'm okay at last, but I don't know if that can erase all the past. And the pettiness, a reflection of the emptiness. Hilarious, you think you're worth my time, you're delirious. Mysterious, because you hide behind a fake exterior. Inferior, you know I'll always be a bit superior. Get off of me, this ain't no humble brag. I want you to hear words, you can say them back. I want you to feel free from the chains at last, and to believe in what you got, it was built to last, yeah.
IPv4 is facing some serious limitations, and it's becoming increasingly clear. First off, with the explosion of internet-connected devices, we're nearly out of addresses. NAT, or Network Address Translation, has been a lifesaver, letting us use private IPs to stretch that dwindling pool. But that's just a band-aid on a much bigger problem. Then there's the lack of built-in security. IPv4 doesn't support encryption or authentication natively, leaving our data vulnerable. It's like sending postcards instead of sealed letters. Anyone can read them. And let's not forget how inefficient it is for modern networks. Limited multicast support and a lack of quality of service for real-time traffic mean that streaming and gaming can suffer. As we push further into the digital age, these limitations are becoming harder to ignore. We need to rethink our approach to internet addressing and security before it's too late. IPv4 has some undeniable advantages that make it a cornerstone of our internet infrastructure. First off, its simplicity is a game changer. The straightforward design allows even those new to networking to grasp the concepts quickly and deploy it with ease. Then there's the widespread adoption. Almost every device and network supports IPv4, creating a seamless connection across the globe. This ubiquity means that whether you're on a smartphone, a laptop, or any other device, you can count on IPv4 to keep you connected. Finally, let's talk about efficient routing. IPv4 is optimized for global-scale networks, ensuring that data packets find their way swiftly and reliably. This efficiency is crucial as we continue to expand our digital landscape. In a world where connectivity is key, IPv4 remains a vital player. IPv4 has some undeniable advantages that make it a cornerstone of our internet infrastructure.